The universe contains more galaxies than there are grains of sand on every beach on Earth. Each galaxy is a gravitationally bound system composed of stars, gas, dust, and dark matter, rotating within its own massive halo. Some form structured spiral arms shaped by density waves, others evolve into elliptical galaxies dominated by older stellar populations, and many remain so faint that only modern deep field surveys can detect them. The brightest galaxies emit light that travels billions of years before reaching our telescopes. Galaxies also interact through tidal forces, triggering star formation, stripping material, and sometimes merging over hundreds of millions of years. For most of history, they were misidentified as nebulae, until Edwin Hubble proved in the 1920s that these objects lie far beyond the Milky Way. Current estimates suggest roughly 2 trillion galaxies in the observable universe, yet much about their formation, evolution, and dark matter structure remains unresolved. The spiral giants that dominate the cosmos. Spiral galaxies are the superstars of the universe, the ones that appear in posters, documentaries, and textbooks. They're instantly recognizable. A bright central bulge, surrounded by sweeping arms that curve outward in elegant arcs, studded with brilliant blue regions where new stars are being born. These are the galaxies that capture the imagination because they look alive, dynamic, as if they're actively doing something rather than just sitting there. And in a sense, they are. Spiral galaxies are the factories of the cosmos, churning out new stars at a steady pace, recycling gas and dust through generations of stellar birth and death. The Milky Way, our home galaxy, is a spiral. It stretches about 100,000 light-years from edge to edge and contains somewhere between 200 and 400 billion stars, though the exact number is frustratingly hard to pin down because we're stuck inside it, trying to map its structure from within. Imagine trying to draw a map of a forest while standing in the middle of it, surrounded by trees in every direction, and you'll get a sense of the challenge astronomers face. What we do know is that the Milky Way has at least 4 major spiral arms: the Perseus arm, the Scutum-Centaurus arm, the Norma arm, and the Sagittarius arm. Our Sun sits in a minor spur called the Orion arm, about 26,000 light-years from the galactic center, orbiting at a leisurely 230 kilometers per second. At that speed, it takes about 225 million years to complete one full orbit, a period astronomers call a galactic year. The last time the Sun was in this position, dinosaurs hadn't even evolved yet. But here's something strange about spiral arms. They're not solid structures. The stars in a spiral galaxy don't stay in the arms like cars stuck in a lane on a highway. Instead, they drift in and out, passing through the arms as they orbit the galactic center. The arms themselves are actually density waves, regions where stars and gas temporarily bunch up due to gravitational interactions, like traffic jams that move through the disk. As stars enter a spiral arm, they slow down slightly, creating the appearance of a bright, defined structure. Young, massive blue stars form in these arms because the density waves compress gas clouds, triggering star formation. These stars burn hot and die fast, so they never get a chance to drift far from where they were born. That's why spiral arms glow blue, while the regions between them look more yellow and red, populated by older, longer-lived stars. The Andromeda Galaxy, officially known as Messier 31 or M31, is the nearest large spiral galaxy to the Milky Way, sitting about 2.5 million light-years away. It's bigger than the Milky Way, containing roughly 1 trillion stars, and it's heading straight toward us. Don't panic, the collision won't happen for another 4.5 billion years, and when it does, the stars are so far apart that very few will actually hit each other. Instead, the two galaxies will pass through each other like ghosts, their gravity pulling and stretching both into long tidal tails before they eventually merge into a single giant elliptical galaxy. Astronomers have already given this future merger a name: Milkomeda. On a clear night, far from city lights, you can see Andromeda with the naked eye as a faint, fuzzy patch in the constellation Andromeda. The light hitting your eyes left that galaxy 2.5 million years ago, when our ancestors were just learning to use stone tools. Not all spiral galaxies look the same. About 2/3 of them, including the Milky Way and Andromeda, are barred spirals, meaning they have a straight bar of stars running through their center, with the spiral arms emerging from the ends of the bar rather than from the nucleus itself. The bar is thought to form when gravitational instabilities in the disk cause stars to migrate inward and outward in an organized way, creating an elongated structure. Bars aren't permanent. They can grow, shrink, or even disappear over hundreds of millions of years as the galaxy's mass distribution shifts. The Milky Way's bar is about 27,000 light-years long and rotates as a rigid structure, completing one rotation every 200 million years or so. Some spiral galaxies have arms that wind tightly around the center, while others have loose, floppy arms that barely make half a turn before fading away. Astronomers classify spirals based on how tight their arms are and how big their central bulge is, using a system developed by Edwin Hubble. Galaxies with large bulges and tightly wound arms are called SA galaxies. Those with smaller bulges and more open arms are SB galaxies, and those with tiny bulges and loose, ragged arms are SC galaxies. The Milky Way is probably an SBC, meaning it's a barred spiral with a small bulge and fairly open arms, though again, mapping it from inside makes it hard to be certain. The spiral galaxy, Messier 51, also called the Whirlpool Galaxy, is one of the most photographed galaxies in the sky, and for good reason. It's nearly face-on from our perspective, about 23 million light-years away, and it has a small companion galaxy, NGC 5195, that appears to be tugging on one of its spiral arms, stretching it outward in a beautiful gravitational interaction. The Whirlpool's arms are packed with pinkish regions of ionized hydrogen gas, marking areas where massive young stars are blasting their surroundings with ultraviolet radiation. This galaxy is a textbook example of a grand design spiral, a type where the arms are prominent, well-defined and symmetrical, likely shaped by the gravitational influence of the companion galaxy. Most spirals aren't this neat. The majority are flocculent spirals, where the arms are fragmented and patchy with no clear pattern, looking more like tufts of cotton than sweeping arcs. Then there's Messier 74, a stunning face-on spiral about 30 million light-years away in the constellation Pisces. It has two main arms that wind outward in near-perfect symmetry, glowing with clusters of young blue stars and pink nebulae. Despite its beauty, M74 is notoriously difficult to see through amateur telescopes because it has a very low surface brightness. Its light is spread out over a large area, making it look faint and washed out compared to more compact galaxies. Astrophotographers love it though, because long-exposure images reveal its intricate structure in stunning detail. NGC 1300 is one of the finest examples of a barred spiral galaxy, located about 61 million light-years away. Its bar is so prominent and well-defined that it looks almost artificial, like something constructed rather than naturally formed. At the center of the bar is a smaller spiral structure, a sort of galaxy within a galaxy, where gas is funneled inward by the bar's gravity and forms a mini-spiral around the supermassive black hole at the nucleus. This kind of nested structure hints at the complex dynamics at play inside galaxies, where gravitational forces act on multiple scales simultaneously. Not all spirals are massive. The Triangulum Galaxy, or Messier 33, is the third largest member of our local group of galaxies, after Andromeda and the Milky Way, but it's much smaller, containing only about 40 billion stars. It's about 2.7 million light-years away and is gravitationally bound to Andromeda, likely orbiting it as a satellite. Triangulum is a pure spiral with no bar, and its arms are loose and fragmented, dotted with enormous star-forming regions. One of them, NGC 604, is one of the largest known stellar nurseries in the local group, spanning about 1,500 light-years and containing more than 200 of the hottest, most massive stars known. If NGC 604 were as close to us as the Orion Nebula, it would cast shadows on Earth. Spiral galaxies are powered by a delicate balance. They need a steady supply of cold gas to keep forming stars, but they also need enough dark matter to hold everything together and maintain the rotation curve. Without dark matter, the outer regions of spiral galaxies would fly apart because the visible matter alone doesn't provide enough gravity to keep stars in orbit at the speeds we observe. This was one of the first major pieces of evidence for dark matter. Astronomers measured the rotation speeds of stars in spiral galaxies and found that instead of slowing down at greater distances from the center, as they should if only visible matter were present, the speed stayed constant or even increased slightly. The only explanation was that galaxies are embedded in massive halos of invisible matter, extending far beyond the visible disk. The ancient ellipticals that forgot how to make stars. Elliptical galaxies are the complete opposite of spirals. Where spirals are flat, dynamic, and full of gas and young stars, ellipticals are three-dimensional, static, and mostly devoid of star formation. They range in shape from nearly spherical to highly elongated footballs, and they come in an enormous range of sizes, from dwarfs containing just a few million stars to supergiant ellipticals with trillions. They're the retirement homes of the universe, populated almost entirely by old red stars that formed billions of years ago and have been quietly burning ever since. There are no blue stars, no pink nebula, no signs of active star formation. Just an ancient stellar population slowly aging toward oblivion. The largest galaxies in the universe are all ellipticals. IC 1101, located about 1.07 billion light-years away in the constellation Virgo, is one of the biggest known galaxies, with a diameter of roughly 6 million light-years, about 60 times the size of the Milky Way. It contains an estimated 100 trillion stars, more than the Milky Way and Andromeda combined by a factor of 50. IC 1101 sits at the center of a massive galaxy cluster, where it's been cannibalizing smaller galaxies for billions of years, growing larger and larger like a cosmic vacuum cleaner. Its core is so bright that it outshines everything else in the cluster, but its outer regions fade gradually into space with no clear boundary, blending into the faint glow of intra-cluster light produced by stars ripped from other galaxies during interactions. Elliptical galaxies don't rotate the way spirals do. In a spiral galaxy, most of the stars orbit in the same direction, confined to a flat disk. In an elliptical, stars move in all directions. Their orbits a chaotic swarm of crisscrossing paths with no preferred orientation. Some stars plunge toward the center on radial orbits, while others loop around the outer edges. The net result is a galaxy that looks the same from almost any angle, a smooth, featureless blob of starlight. This random motion is supported by the galaxy's overall gravitational field rather than by organized rotation, which is why ellipticals don't flatten into disks the way spirals do. The most likely explanation for how elliptical galaxies form is that they're the product of galaxy mergers. When two spiral galaxies collide, their disks are disrupted, their spiral arms shredded, and their gas clouds compressed and heated. The collision triggers intense bursts of star formation, using up most of the available gas in a few 100 million years. What's left afterward is a bloated, gas-poor elliptical galaxy full of stars, but with no fuel to make new ones. Computer simulations of galaxy mergers reproduce this process beautifully, showing how two neat spirals can smash together and produce a lumpy, chaotic elliptical. Over time, gravitational interactions even out the lumpiness, and the galaxy relaxes into a smooth, symmetric shape. Messier 87, located about 53 million light-years away in the Virgo cluster, is one of the most famous elliptical galaxies and one of the most massive galaxies in the nearby universe. It contains around 1 trillion stars and has a diameter of about 240,000 light-years. But M87 is famous for something else, its supermassive black hole. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, and the black hole in question was the one at the heart of M87. With a mass of 6.5 billion times that of the Sun, this black hole is actively feeding on surrounding gas, producing a brilliant jet of superheated plasma that shoots out from its vicinity at nearly the speed of light, extending for at least 5,000 light-years into space. The jet is so energetic that it glows brightly in radio waves, X-rays, and even visible light, making M87 one of the brightest radio sources in the sky, despite being tens of millions of light-years away. Centaurus A, or NGC 5128, is another elliptical galaxy with a bizarre twist. Located about 12 million light-years away, It's the fifth brightest galaxy in the sky and one of the closest giant ellipticals to Earth. What makes it strange is the dark dust lane that cuts across its center, a thick band of gas and dust that seems completely out of place in an elliptical galaxy. The explanation is that Centaurus A recently devoured a smaller spiral galaxy. The dust lane is the remnant of that galaxy's disk, still visible even though the merger happened millions of years ago. The collision reignited star formation in parts of Centaurus A, creating pockets of young blue stars mixed in with the old red population. Like M87, Centaurus A has a supermassive black hole at its center that's producing powerful jets of plasma, making it one of the brightest radio galaxies in the sky. Not all ellipticals are giants. Dwarf elliptical galaxies, often abbreviated as DEs, are small, faint galaxies with only a few million to a few billion stars. They're incredibly common, especially in galaxy clusters, where they swarm around larger galaxies like flies around a porch light. Many dwarf ellipticals are thought to be the remnants of larger galaxies that were stripped of their outer stars by tidal forces during close encounters with more massive neighbors. Others may be ancient, low-mass galaxies that formed early in the universe and never grew very large. Despite their small size, dwarf ellipticals are important because they contain clues about the building blocks of larger galaxies. The leading theory of galaxy formation, called hierarchical assembly, suggests that large galaxies grew by merging with and accreting smaller ones over billions of years. Dwarf ellipticals might be the survivors of that process, the ones that managed to avoid being eaten. One of the strangest elliptical galaxies is Maffei 1, located just 10 million light-years away in the constellation Cassiopeia. It's one of the closest giant elliptical galaxies to the Milky Way, but you've probably never heard of it because it's hidden behind a thick curtain of dust in the plane of our galaxy, making it almost impossible to see at visible wavelengths. Astronomers only discovered it in 1968, using infrared observations that could penetrate the dust. Maffei 1 is so obscured that its light is dimmed by a factor of 10,000 compared to what we would see if it were in a clear part of the sky. If not for the dust, it would be one of the most prominent galaxies visible from Earth. Elliptical galaxies also exhibit a puzzling correlation between their size and their internal properties. Observations show that the most massive ellipticals have stars that move faster, as expected from their stronger gravity, but the relationship isn't quite what simple physics would predict. Instead, there's a tight correlation between the velocity dispersion of stars, how fast they're moving in random directions, and the galaxy's luminosity. This relationship, called the Faber-Jackson relation, is so tight that astronomers can use it to estimate a galaxy's intrinsic brightness just by measuring how fast its stars are moving, and from that, they can calculate its distance. It's a powerful tool for cosmology, but no one is entirely sure why the relationship is so precise. When galaxies collide and chaos reigns. Galaxy collisions are some of the most dramatic events in the universe, cosmic slow-motion car crashes that play out over hundreds of millions of years. Despite the violence of the process, very few stars actually hit each other during a collision because stars are incredibly tiny compared to the distances between them. A typical galaxy is so empty that if you shrunk the Sun down to the size of a grain of sand, the nearest star would be about 10 kilometers away. So, when two galaxies merge, it's more accurate to say that their stars pass through each other like two swarms of bees interpenetrating, while the gravitational fields of the galaxies do all the real damage, pulling and stretching both into bizarre shapes. The most famous example of a galaxy collision in progress is the Antennae galaxies, a pair of spirals located about 45 million light-years away in the constellation Corvus. They started colliding roughly 600 million years ago, and the encounter has completely disrupted both galaxies, flinging out long tails of stars, gas, and dust that stretch for hundreds of thousands of light-years into space. These tails, which give the system its name because they look like the antennae of an insect, are made of material pulled out of the galaxies by tidal forces, the same gravitational effect that causes ocean tides on Earth, but on a much grander scale. Where the two galaxies overlap, massive clouds of gas have collided and compressed, triggering an explosion of star formation. The antennae galaxies contain thousands of young star clusters, many of them so compact and bright that they'll likely evolve into globular clusters, the ancient spherical swarms of stars that orbit most large galaxies. The cores of the two galaxies haven't merged yet. They're still orbiting each other, spiraling inward as they lose energy to dynamical friction, a process where the gravitational pull of one galaxy drags on the other, sapping momentum from their orbital motion. Eventually, in another few 100 million years, the cores will coalesce into a single nucleus, and the merged galaxy will settle into an elliptical shape. By that time, most of the gas will have been used up in the starburst, and star formation will peter out, leaving behind a red, dead elliptical filled with aging stars. The mice galaxies, officially known as NGC 4676, are another colliding pair, located about 290 million light-years away. Like the antennae, they have long tails of stars stretching out behind them, formed by tidal interactions during their encounter. The two galaxies are in the process of merging, and simulations suggest that they'll complete the merger within the next few 100 million years. What's fascinating about the mice is that detailed studies of their tails reveal streams of stars, gas, and globular clusters that were ripped out of both galaxies and now orbit in the space between them, slowly dispersing into the intergalactic medium. ARP 273 is a stunning example of a collision between two spiral galaxies, located about 300 million light-years away. The larger galaxy, UGC 1810, has been dramatically distorted by its smaller companion, UGC 1813, which appears to have plunged through the disk of the larger galaxy. The collision has drawn out a long, thin tail of stars from UGC 1810 and has sparked intense star formation in the outer regions of the disk, creating a ring of brilliant blue clusters. The smaller galaxy has also been distorted, pulled into an elongated shape by the gravitational forces at play. ARP 273 is a snapshot of a collision in progress, a moment frozen in time showing two galaxies in the act of destroying each other. Not all collisions are between galaxies of similar size. Often, a large galaxy will encounter a much smaller one, and the result is less of a merger and more of a snack. The Milky Way is currently in the process of devouring the Sagittarius dwarf elliptical galaxy, a small galaxy that wandered too close and is now being torn apart by our galaxy's gravity. Streams of stars from the Sagittarius dwarf have been pulled out and wrapped around the Milky Way multiple times, like a ribbon around a maypole. These streams are still visible today as faint looping structures in the halo of the Milky Way, and they're slowly being absorbed into our galaxy's disk. The Sagittarius dwarf will be completely assimilated within the next billion years or so, its stars indistinguishable from the rest of the Milky Way's population. The Tadpole Galaxy, or UGC 10214, is a disturbed spiral galaxy with a tail of stars stretching out behind it for more than 280,000 light-years, 10 times the length of the galaxy's disk. The tail was formed when a smaller galaxy, likely a blue compact dwarf, plunged through the disk of the tadpole about 100 million years ago, pulling out a long streamer of stars and gas in its wake. The intruder galaxy is still visible as a faint blob near the tail, moving away from the tadpole after its violent passage. Over time, the tail will disperse, and the stars will either fall back into the main galaxy or escape into intergalactic space. Galaxy collisions can also trigger the formation of ring galaxies, one of the strangest types of galaxies in the universe. Hogg's object is the most famous example, a nearly perfect ring of bright blue stars surrounding a core of older yellow stars, with a gap of almost empty space in between. The ring is about 120,000 light-years in diameter, roughly the same size as the Milky Way, and it's located about 600 million light-years away. The leading explanation for Hogg's object is that it formed when a small galaxy passed directly through the center of a larger disk galaxy. The collision sent a ripple of density waves propagating outward through the disk, compressing gas and triggering star formation in a ring that expanded away from the point of impact. What makes Hogg's object especially bizarre is that there's no sign of the intruder galaxy. It's either been completely destroyed or has moved far away, leaving only the ring behind as evidence of the collision. The Cartwheel Galaxy, located about 500 million light-years away, is an even more dramatic ring galaxy. It has a bright inner ring, an outer ring, and spoke-like structures connecting them, giving it the appearance of a wagon wheel. The cartwheel formed when a smaller galaxy punched through its disk about 200 million years ago, creating a shock wave that rippled outward and is still propagating today. The outer ring is expanding at about 300,000 kilometers per hour, sweeping up gas and triggering star formation as it goes. Infrared observations reveal hundreds of young star clusters embedded in the outer ring, each containing thousands of hot, massive stars. In another few 100 million years, the rings will fade as the shockwave dissipates, and the cartwheel will gradually settle back into a more normal spiral or irregular shape. The tiny dwarfs that outnumber all others. Dwarf galaxies are the runts of the cosmic litter, small, faint collections of stars that barely qualify as galaxies at all. Some contain only a few thousand stars, not much more than a large globular cluster. Others have a few billion, still tiny compared to giants like the Milky Way or Andromeda. But what dwarf galaxies lack in size, they make up for in numbers. They're by far the most common type of galaxy in the universe, outnumbering large galaxies by at least 10 to 1 and possibly much more. The problem is that most of them are so faint that we can only detect the ones nearby. There could be trillions of dwarf galaxies lurking in the distant universe, too dim to show up in even the deepest images. Dwarf galaxies come in several varieties. Dwarf ellipticals, as mentioned earlier, are small, smooth blobs of old stars with no gas or ongoing star formation. Dwarf irregulars are the opposite, small, messy galaxies with active star formation, often triggered by gravitational interactions with larger neighbors. And then there are the ultra-faint dwarfs, a class of galaxies so dim that they were only discovered in large numbers in the last 2 decades. These are some of the least luminous objects in the universe, fainter than a single star in some cases. Yet they contain hundreds or thousands of stars spread out over a region of space. The Large Magellanic Cloud and Small Magellanic Cloud, visible from the southern hemisphere as 2 fuzzy patches in the night sky, are the most prominent dwarf galaxies near the Milky Way. The Large Magellanic Cloud, or LMC, sits about 160,000 light-years away and contains roughly 30 billion stars. It's classified as a dwarf irregular galaxy, but it has hints of spiral structure, including a faint bar and a single spiral arm. The LMC is a vigorous star-forming galaxy, home to the Tarantula Nebula, the largest and most active star-forming region in the local group. The Tarantula contains some of the most massive stars ever discovered, including R13601, a star with a mass at least 250 times that of the Sun, right at the theoretical limit for how massive a star can get before it tears itself apart. The Small Magellanic Cloud, located about 200,000 light-years away, is smaller and fainter than the LMC, with only about 7 billion stars. It's also less metal-rich, meaning it has a lower abundance of elements heavier than hydrogen and helium. This makes it an interesting laboratory for studying stellar evolution, because its stars resemble the metal-poor stars that dominated the early universe. Both Magellanic Clouds are gravitationally bound to the Milky Way and are being slowly pulled apart by tidal forces. A stream of gas called the Magellanic Stream trails behind them, stretching across more than half the sky, marking the path they've traveled as they orbit our galaxy. The Sagittarius Dwarf Elliptical Galaxy, mentioned earlier, is even closer than the Magellanic Clouds, at a distance of only 70,000 light-years. It's on the opposite side of the Milky Way from the Sun, hidden behind the dense stars and dust of the galactic core, which is why it wasn't discovered until 1994, despite being one of our nearest neighbors. The Sagittarius Dwarf is in the final stages of being torn apart, with long streams of stars wrapping around the Milky Way like scarves. These streams are some of the most prominent structures in the outer halo of our galaxy, and they've helped astronomers map the shape and mass of the Milky Way's dark matter halo. Then there are the ultra-faint dwarfs, the smallest and dimmest galaxies known. Galaxies like Segway 1, Segway 2, and Willman 1 contain only a few hundred to a few thousand stars and are so faint that they're barely brighter than a single bright star. They're spread out over large volumes of space, with such low densities that they're more like clouds of stars than coherent galaxies. Yet despite their small size, ultra-faint dwarfs are incredibly important for cosmology because they're dominated by dark matter. In fact, they're the most dark matter-dominated objects in the universe, with mass-to-light ratios so high that the visible stars contribute almost nothing to the total gravitational mass. Studying these galaxies can help astronomers understand the nature of dark matter and test theories of galaxy formation on the smallest scales. Dwarf spheroidal galaxies are another class of ultra-faint dwarfs, slightly larger and more luminous than the ultra-faints, but still incredibly dim. Draco, Ursa Minor, and Sculptor are all dwarf spheroidals orbiting the Milky Way, each containing a few million stars in a diffuse spherical distribution. They're completely devoid of gas and show no signs of star formation, suggesting that their gas was stripped away long ago, either by interactions with the Milky Way or by energetic processes like supernova explosions early in their history. Dwarf spheroidals are thought to be the building blocks of larger galaxies, the leftover pieces of the hierarchical assembly process that haven't yet been accreted by a giant galaxy. Leo Britois is a dwarf spheroidal about 820,000 light-years from the Milky Way, one of the more distant members of our local group. Despite being at the edge of the Milky Way's gravitational influence, Leo has a very high velocity dispersion for its size, indicating that it's unusually massive for its luminosity. This suggests it's embedded in a heavy dark matter halo, further evidence that dwarf galaxies are crucial for understanding dark matter. The Fornax dwarf spheroidal is another satellite of the Milky Way, located about 460,000 light-years away. What makes Fornax unusual is that it contains 6 globular clusters, a huge number for such a small galaxy. In contrast, the Sagittarius dwarf elliptical, which is much larger and more luminous, has only 4 globular clusters. This raises an interesting puzzle. Why does Fornax have so many? One possibility is that Fornax formed in a denser environment early in the universe, where globular cluster formation was more efficient. Alternatively, the globular clusters might be the remnants of smaller galaxies that Fornax accreted, the cores of tidally stripped dwarfs that merged with Fornax in the distant past. Some dwarf galaxies are loners, isolated from any large galaxy and drifting alone through intergalactic space. Leo A is a dwarf irregular galaxy about 2.5 million light-years away, far outside the main concentration of the local group. It's been isolated for most of its life, which has allowed it to retain a large reservoir of neutral hydrogen gas, despite being relatively old. Leo A is still forming stars today, though at a low rate, and it's one of the most metal-poor galaxies in the local group, indicating that it hasn't gone through many generations of star formation. Isolated dwarfs like Leo A are valuable because they haven't been disturbed by interactions with larger galaxies, so they preserve a more pristine record of their formation and early evolution. Dwarf galaxies are also the primary targets in the search for dark matter annihilation or decay signals. Because they're so dominated by dark matter and contain so few stars, any unexpected gamma-ray or X-ray emission from a dwarf spheroidal would be a strong hint of dark matter interactions. Astronomers have been using gamma-ray telescopes to observe dozens of dwarf galaxies, looking for faint glows that can't be explained by ordinary astrophysical processes. So far, the searches have come up empty, but they've placed important limits on the properties of dark matter particles. The ghostly ultra-diffuse galaxies that almost vanish. In 2015, astronomers discovered a new class of galaxies that seemed impossible. Galaxies as large as the Milky Way, but with only about 1% of its stars. These ultra-diffuse galaxies, or UDGs, are so spread out that they're almost invisible, their feeble light diluted over such a large area that they barely show up even in deep images. They're the ghosts of the galaxy world, present but almost impossible to see, and their existence has forced astronomers to rethink what a galaxy can be. Ultra-diffuse galaxies were first found in the Coma Cluster, a massive cluster of galaxies about 300 million light-years away. Using the Dragonfly telephoto array, a specialized telescope designed to detect extremely faint extended objects, astronomers identified 47 large diffuse galaxies that had been missed by previous surveys. These galaxies have diameters similar to the Milky Way, around 60,000 light-years, but they contain so few stars that their total luminosity is only about 1% of the Milky Way's. Their surface brightness is so low that they're fainter than the night sky itself, which makes them incredibly difficult to spot. The existence of ultra-diffuse galaxies raises an immediate question. How did they get so big and so faint? Normally, you'd expect a galaxy with so few stars to be small, like a dwarf spheroidal. The fact that UDGS are large suggests they have a lot of dark matter, enough to hold together a structure the size of a normal galaxy, even though there aren't many stars. Indeed, measurements of the internal motions of stars in some UDGs confirm that they have high mass-to-light ratios, consistent with being dark matter-dominated. But that doesn't explain how they ended up with so few stars in the first place. One theory is that UDGS are failed galaxies, objects that started to form like normal galaxies, but had their star formation shut down early, perhaps by strong winds from supernovae or by the intense radiation from nearby galaxies in a cluster environment. Without ongoing star formation, the galaxies would remain faint while continuing to grow in size through gravitational interactions and the accretion of dark matter. Another idea is that UDGS are the remnants of galaxies that were puffed up by tidal interactions with larger galaxies. Close encounters with a massive galaxy can inject energy into a smaller one, causing its stars to spread out over a larger volume and lowering its surface brightness. Over time, repeated interactions could inflate a dwarf galaxy into an ultra-diffuse galaxy. One of the most studied ultra-diffuse galaxies is Dragonfly 44, located in the Coma cluster. It's about the same size as the Milky Way, but contains only 0.1% as many stars, making it almost entirely dark matter. In fact, measurements suggest that 99.99% of Dragonfly 44's mass is dark matter, one of the highest proportions ever measured in any galaxy. Despite having so few stars, Dragonfly 44 has a large population of globular clusters, about 94 of them, which is roughly the same number as the Milky Way. This is bizarre because normally the number of globular clusters scales with the total stellar mass of a galaxy, but Dragonfly 44 has far more globular clusters than it should for its luminosity. The globular clusters might be the key to understanding how UDGS form, possibly representing bursts of star formation that occurred early in the galaxy's history before something shut down further star formation. Not all ultra-diffuse galaxies are in clusters. Some have been found in lower density environments, including in the local group. Antlia 2 is a massive ultra-diffuse galaxy orbiting the Milky Way at a distance of about 420,000 light-years. It's enormous, with a diameter of roughly 170,000 light-years, making it one of the largest satellites of the Milky Way. Yet it's so faint that it wasn't discovered until 2018, hidden behind the disk of our galaxy. Antlia 2 contains only a few million solar masses worth of stars, but has a total mass of about 10 billion solar masses, almost all of it dark matter. Its existence so close to the Milky Way suggests that ultra-diffuse galaxies might be more common than previously thought, just very hard to detect. The mystery of ultra-diffuse galaxies is far from solved. Some appear to be dark matter dominated, while others seem to have normal amounts of dark matter, or even less than expected. NGC 1052-DF2, an ultra-diffuse galaxy about 65 million light-years away, made headlines in 2018 when astronomers announced that it appeared to contain little or no dark matter at all. This was shocking, because dark matter is supposed to be essential for galaxy formation, and a galaxy without it shouldn't exist according to standard theory. Follow-up studies have been controversial, with some researchers arguing that the galaxy is closer than originally thought, which would make it smaller and less unusual, while others maintain that it really is a dark matter-free galaxy, perhaps formed through a violent interaction that stripped away its dark matter halo. Ultra-diffuse galaxies are teaching us that galaxies can exist in a much wider range of forms than we previously imagined. They challenge our understanding of how galaxies form and evolve, And they're forcing astronomers to develop new theories to explain how you can have a galaxy the size of the Milky Way with almost no stars, or a galaxy with no dark matter at all. Every new discovery adds another piece to the puzzle, but the picture is still far from complete. The violent starburst galaxies. Most galaxies form stars at a leisurely pace, converting a few solar masses of gas into stars each year and spreading that process out over billions of years. But some galaxies are in a hurry. Starburst galaxies are forming stars at rates hundreds or even thousands of times higher than normal, burning through their gas reservoirs in just a few tens of millions of years. These galaxies are the cosmic equivalent of someone spending their entire paycheck in a single night. Brilliant, intense, and destined to burn out fast. Starburst galaxies are usually triggered by some kind of gravitational disturbance. The most common trigger is a galaxy collision or close encounter, which compresses gas clouds and drives them toward the center of the galaxy, where they pile up and collapse to form stars. Collisions can also drive gas inflows by disrupting the orderly rotation of a galaxy's disk, funneling material inward where it accumulates in the nucleus. The result is a brief but spectacular period of star formation, with thousands of massive stars being born in a relatively small region of space. Messier 82, also known as the Cigar Galaxy, is one of the nearest and best-studied starburst galaxies, located about 12 million light-years away in the constellation Ursa Major. It's undergoing a starburst triggered by its interaction with its larger neighbor, Messier 81. The gravitational pull of M81 has stirred up the gas in M82, funneling it toward the center and igniting an intense burst of star formation. The core of M82 is forming stars at a rate about 10 times higher than the entire Milky Way, churning out massive stars that live fast and die young in spectacular supernova explosions. The supernova rate in M82 is so high that the combined energy from stellar winds and supernova blasts has blown a huge cavity in the surrounding gas, creating a superwind that blasts material out of the galaxy at speeds of several million kilometers per hour. This outflow is visible as glowing filaments of ionized gas, extending thousands of light years above and below the plane of the galaxy, creating a structure that looks like a fountain. The superwind is so powerful that it's ejecting gas into intergalactic space, enriching the surrounding medium with heavy elements forged in the cores of massive stars. In the process, M82 is blowing away the very fuel it needs to keep forming stars, ensuring that the starburst will be short-lived. ARB 220 is an even more extreme starburst galaxy, located about 250 million light-years away. It's the result of a merger between two gas-rich spiral galaxies that began colliding about 700 million years ago. The merger drove enormous amounts of gas into the center of the system, where it's now forming stars at a prodigious rate, estimated at several hundred solar masses per year. The core of ARB 220 is completely obscured by thick clouds of dust, making it invisible at optical wavelengths, but infrared and radio observations reveal a double nucleus, the remnants of the two original galaxy cores that haven't yet fully merged. Each nucleus is a compact starburst region, packed with newly formed stars and surrounded by dense clouds of molecular gas. The starburst in ARB 220 is so intense that it's using up gas faster than it can be replenished, and the galaxy will exhaust its fuel within the next few tens of millions of years. When that happens, star formation will shut down, and ARB 220 will fade into a red, dead elliptical galaxy filled with aging stars. But before that happens, the starburst will produce thousands of supernovae, further enriching the gas and possibly triggering additional waves of star formation in the outer regions of the galaxy. The antennae galaxies, discussed earlier, are also undergoing a starburst as a result of their ongoing merger. The collision has compressed gas clouds in the overlap region between the two galaxies, triggering the formation of thousands of massive star clusters, some containing 1 million stars or more. These superstar clusters are extremely compact and bright, and many of them will survive the merger to become globular clusters, the ancient stellar swarms that orbit large galaxies. Observations of the antennae have revealed that the starburst is concentrated in specific regions where the gas density is highest, while other parts of the merging system are relatively quiescent. NGC 253, also known as the Sculptor Galaxy, is another nearby starburst, located about 11 million light-years away. Like M82, it has a powerful superwind blowing out of its core, driven by the combined energy of supernova and stellar winds from massive stars. The nucleus of NGC 253 is heavily obscured by dust, but infrared and radio observations reveal intense star formation in a compact region less than 1,000 light-years across. The starburst is thought to have been triggered by gravitational instabilities in the galaxy's disk that drove gas inward, rather than by an interaction with another galaxy. Starburst galaxies are important for understanding galaxy evolution because they represent periods of rapid transformation. A galaxy that was once gas-rich and slowly forming stars can be converted into a gas-poor, quiescent galaxy in just a few tens of millions of years by a starburst event. This process is thought to be one of the main mechanisms that quenches star formation in galaxies and converts spirals into ellipticals. By studying starbursts, astronomers can see this transformation happening in real time, rather than having to infer it from populations of old stars. Infrared observations from space telescopes like Spitzer and Herschel have revealed that starburst galaxies are even more common in the distant universe than in the nearby universe. When we look at galaxies billions of light-years away, we're seeing them as they were billions of years ago. And at those early times, galaxy mergers and interactions were much more frequent because galaxies were packed more closely together. As a result, the average star formation rate in the universe was much higher in the past, and starburst galaxies contributed a significant fraction of all the stars that formed during the peak era of galaxy formation, roughly 10 billion years ago. Some starburst galaxies are so dusty and so heavily obscured that they're almost invisible at optical wavelengths but incredibly bright in the infrared. These ultraluminous infrared galaxies, or ULIRGs, emit more than 90% of their light in the infrared, making them among the most luminous galaxies in the universe. Many ULIRGs are merging systems where gas has been driven into a compact nuclear region, forming stars at rates of hundreds or even thousands of solar masses per year. The newly formed stars heat the surrounding dust, which re-radiates the energy as infrared light, creating the intense infrared glow that defines these objects. ARP 299 is a pair of colliding galaxies, about 140 million light-years away, that's transitioning into a ULIRG. The two galaxies are in the process of merging, and the collision has triggered intense star formation in multiple regions throughout the system. X-ray observations have revealed that ARP 299 also contains several actively feeding supermassive black holes, adding to the energy output of the system. The combination of starburst activity and black hole accretion makes ARP 299 one of the most energetic systems in the nearby universe. The blazing hearts of active galactic nuclei. At the centers of most large galaxies lurks a supermassive black hole, an object with a mass ranging from millions to billions of times that of the Sun, compressed into a region smaller than our solar system. Most of the time, these black holes are quiet, gently sipping material from their surroundings at a slow pace. But sometimes they wake up and begin feeding voraciously, pulling in gas at enormous rates and releasing energy that can outshine the entire galaxy. When this happens, the galaxy becomes what astronomers call an active galactic nucleus, or AGN, one of the most powerful and spectacular phenomena in the universe. Active galactic nuclei come in many varieties, classified based on their brightness, their spectrum, and the angle at which we view them. Seyfert galaxies are spiral galaxies with bright, point-like nuclei that vary in brightness over timescales of days to years. Quasars are extremely luminous AGN, visible across billions of light-years, powered by black holes accreting material at close to the maximum possible rate. Radio galaxies are giant ellipticals with powerful jets of plasma shooting out from their cores at nearly the speed of light, creating enormous lobes of radio emission that can extend for millions of light-years. Blazars are AGN, whose jets point directly at Earth, making them appear incredibly bright and variable as the jet's emission is boosted by relativistic beaming effects. The mechanism powering all AGN is the same: accretion onto a supermassive black hole. As gas spirals inward toward the black hole, it forms an accretion disk, a flat, rotating structure where gravitational energy is converted into heat through friction. The inner regions of the disk heat up to millions of degrees, hot enough to emit X-rays and ultraviolet light. Some of the material in the disk is channeled into narrow jets that shoot out perpendicular to the disk, accelerated to nearly the speed of light by magnetic fields, twisted up by the rotation of the black hole and disk. The jets plow through the surrounding gas, creating shock waves and radio-emitting lobes that can grow larger than the host galaxy itself. NGC 1275, also known as Perseus A, is a giant elliptical galaxy at the center of the Perseus cluster, about 240 million light-years away. It's one of the brightest radio sources in the sky, powered by a supermassive black hole with a mass of about 800 million solar masses. The black hole is actively accreting material, and the energy released is blowing giant bubbles in the hot gas that fills the Perseus cluster. These bubbles are visible in X-ray images as dark cavities surrounded by bright rims, where the expanding jets have pushed aside the cluster gas. The bubbles are enormous, each spanning tens of thousands of light-years, and they contain enough energy to power the entire Milky Way for millions of years. Yet despite the huge energy output, NGC 1275 is barely forming any stars. Its starburst activity shut down by the AGN, which heats the gas and prevents it from cooling and collapsing to form new stars. Centaurus A, mentioned earlier, is another AGN-powered galaxy. Its central black hole is feeding on material left over from the recent merger that created the dust lane, and the energy released is driving powerful jets that extend for nearly 1 million light-years into space. The jets are visible at radio wavelengths, and observations at different wavelengths reveal a complex structure of knots and filaments where the jets interact with the surrounding medium. Centaurus A is one of the closest AGN to Earth, making it an ideal laboratory for studying the physics of black hole accretion and jet formation. Quasars are the most luminous type of AGN, so bright that they can outshine their entire host galaxy. The first quasars were discovered in the 1960s as star-like objects with extremely unusual spectra and enormous redshifts, indicating they were billions of light-years away. The fact that something so distant could appear so bright meant it had to be extraordinarily luminous, and the only known mechanism that could produce that much energy was accretion onto a supermassive black hole. A typical quasar emits as much energy as 1 trillion suns, all from a region no larger than our solar system. 3C273 is the brightest quasar in the sky, located about 2.4 billion light-years away in the constellation Virgo. Despite its enormous distance, it's bright enough to be seen in a small telescope, shining at a magnitude of about 12.8. The central black hole has a mass of about 900 million solar masses and is accreting material at a rate of several solar masses per year. The energy released by this accretion heats the surrounding gas to millions of degrees and powers a jet that extends for hundreds of thousands of light-years. 3C273 was one of the first quasars to be identified, and it played a crucial role in establishing that quasars were powered by supermassive black holes rather than some exotic new form of matter or energy. Most quasars are found at high redshifts, meaning they existed when the universe was young. The peak era of quasar activity occurred about 10 billion years ago, around the same time that the star formation rate in the universe was at its highest. This is not a coincidence. Both quasar activity and star formation require large amounts of gas, and both were more common in the past when galaxies were richer in gas, and mergers were more frequent. Today, most supermassive black holes are dormant, having consumed or expelled most of the gas in their vicinity, and quasars are correspondingly rare. Blazars are AGN, whose jets point almost directly at Earth, making them appear exceptionally bright due to relativistic beaming. When material in a jet moves toward us at close to the speed of light, its light is compressed and intensified, making the jet appear much brighter than it would if it were moving sideways. Blazars are extremely variable, brightening and fading on timescales of hours to days as blobs of material move down the jet and encounter obstacles or magnetic field changes. Some blazars are so bright that they can be detected by gamma-ray telescopes, emitting photons with energies millions of times higher than visible light. BL Lacerti, the prototype of the BL Lac class of blazars, is located about 900 million light-years away. It's so variable that when it was first discovered, astronomers thought it was a variable star in our own galaxy. Only later did they realize it was an extragalactic object, a galaxy with a jet pointing almost directly at us. BL Lac varies in brightness by more than a factor of 15 over periods of a few years, and shorter-term variations of 10 to 20% can occur in a single night. This rapid variability tells us that the emitting region must be very small, no more than a few light hours across, because an object can't vary faster than the light travel time across its size. Radio galaxies like Cygnus A showcase the full extent of AGN jets. Cygnus A, located about 600 million light-years away, is one of the brightest radio sources in the sky, despite its great distance. Its jets have carved out enormous lobes of radio-emitting plasma on either side of the host galaxy, each lobe spanning hundreds of thousands of light-years. The lobes are visible because the jets accelerate electrons to nearly the speed of light, and when these electrons spiral around magnetic field lines, they emit radio waves through a process called synchrotron radiation. The total energy contained in the lobes is staggering, equivalent to the mass energy of several million suns, all produced by material falling into a black hole at the galaxy's center. The galactic cities called clusters. Galaxies are social creatures. They rarely live alone, instead gathering in groups and clusters that can contain anywhere from a few dozen to thousands of galaxies, all bound together by gravity. These cosmic cities are some of the largest structures in the universe, and they're laboratories for studying how galaxies interact, evolve, and transform over billions of years. The Virgo cluster is the nearest large galaxy cluster, sitting about 54 million light-years away and containing more than 1,500 galaxies. It dominates the local universe gravitationally, and even the Milky Way feels its pull, causing our local group of galaxies to drift slowly toward Virgo at about 400 kilometers per second. The cluster is centered on the giant elliptical galaxy Messier 87, whose supermassive black hole and powerful jets make it one of the most studied galaxies in astronomy. Around M87 swarm hundreds of smaller ellipticals, lenticulars, and spirals, all orbiting within the cluster's deep gravitational well. The Virgo cluster is a harsh environment for spiral galaxies. As they fall into the cluster, spirals encounter a hot, diffuse gas called the intracluster medium, which fills the space between galaxies. This gas is extremely thin by terrestrial standards, far more tenuous than the best vacuum we can create on Earth. But because galaxies move through it at such high speeds, the ram pressure is enough to strip away their gas, like a strong wind blowing leaves off a tree. Once stripped of gas, a spiral galaxy can no longer form stars, and it gradually fades into a red dead lenticular or elliptical galaxy. This process, called ram pressure stripping, is one of the main ways that galaxy clusters transform their members. NGC 4522 is a spiral galaxy in the Virgo cluster that's being ram pressure stripped right now. Images show long streamers of gas trailing behind the galaxy as it plows through the intracluster medium, its star-forming material being ripped away and left behind in its wake. Star formation in NGC 4522 has nearly ceased except for a few regions on the leading edge of the disk, where the compression from the ram pressure is actually triggering new bursts of star formation before the gas is lost entirely. Within a few 100 million years, NGC 4522 will be a gas-poor lenticular, unrecognizable as the spiral it once was. The Coma cluster is even larger and more distant than Virgo, sitting about 300 million light-years away and containing more than 1,000 large galaxies plus thousands of dwarfs. It's one of the richest clusters in the nearby universe, and it played a historic role in the discovery of dark matter. In the 1930s, Swiss astronomer Fritz Zwicky measured the velocities of galaxies in the Coma cluster and found that they were moving far too fast to be held together by the gravity of the visible matter alone. He calculated that the cluster must contain about 400 times more mass than could be accounted for by the galaxies themselves, and he proposed that this missing mass was some form of dark matter. His result was largely ignored at the time, but later observations confirmed that clusters do indeed contain enormous amounts of dark matter, far more than the galaxies and hot gas combined. The Coma cluster is filled with a hot, intra-cluster medium that emits X-rays. Heated to tens of millions of degrees by the gravitational energy released as galaxies and gas fall into the cluster. This hot gas contains more ordinary matter than all the stars in all the galaxies in the cluster combined, making it the dominant component of baryonic matter in clusters. The pressure of the hot gas is high enough to prevent galaxy-sized clouds of gas from collapsing to form new stars, which is another reason why clusters are such hostile environments for star formation. The Bullet cluster, located about 3.7 billion light-years away, provided some of the most direct evidence for dark matter. The Bullet cluster is actually two clusters that collided about 150 million years ago at high speed. The collision ripped the clusters apart, and observations show that the hot gas from each cluster collided and slowed down, while the galaxies and dark matter passed through each other largely unaffected, like two swarms of bees interpenetrating. Gravitational lensing measurements reveal that the majority of the mass in the system is not where the gas is, but where the galaxies are, showing that the dark matter halos of the clusters moved right through the collision while the ordinary matter was left behind. This spatial separation of the dark matter and ordinary matter is hard to explain with alternative theories of gravity, making the Bullet cluster one of the strongest pieces of evidence that dark matter is real. Galaxy clusters are connected to each other by filaments of galaxies and dark matter, forming a structure called the cosmic web. The filaments are long, thin structures that can stretch for hundreds of millions of light years, connecting clusters together like threads in a vast spider web. Between the filaments are enormous voids, regions that are mostly empty of galaxies. The cosmic web is a direct consequence of the distribution of dark matter in the early universe. Small fluctuations in the dark matter density grew over time through gravity, pulling more matter into the densest regions and creating the filaments and clusters we see today. The Shapley supercluster is one of the largest concentrations of galaxies in the nearby universe, containing more than 8,000 large galaxies spread across a region about 650 million light-years away. It's so massive that it exerts a significant gravitational pull on the Milky Way, contributing to our motion through space. The supercluster contains dozens of individual galaxy clusters, all connected by filaments and falling together under their mutual gravitational attraction. Over billions of years, these clusters will merge, eventually forming a single, gigantic cluster containing tens of thousands of galaxies. The Sloan Great Wall is one of the largest known structures in the universe, a vast filament of galaxies stretching about 1.4 billion light-years across. It's not a solid wall, but rather a complex of superclusters and filaments that happen to line up in a way that creates an enormous coherent structure. Discoveries like the Sloan Great Wall challenge our understanding of structure formation in the universe, because such large structures shouldn't have had time to form in the 13.8 billion years since the Big Bang, at least according to some models. The existence of these giant structures tells us that the universe is more complex and more richly structured than simple models predict. The lenticular galaxies. Lenticular galaxies occupy an awkward middle ground between spirals and ellipticals, and for a long time, astronomers weren't quite sure what to make of them. They have the flat, disc-like shape of a spiral galaxy and often a prominent central bulge, but they lack spiral arms and have little or no gas or ongoing star formation, like ellipticals. They're labeled S0 in the Hubble classification scheme, positioned at the fork between spirals and ellipticals, and they're surprisingly common, making up about 20% of all galaxies in the nearby universe. The defining feature of a lenticular galaxy is its smooth, featureless disk. Where a spiral galaxy has arms, dust lanes, and bright knots of star formation, a lenticular galaxy has nothing but a uniform glow of old yellow and red stars. Some lenticulars have faint dust lanes or weak spiral structure visible in infrared or ultraviolet images, hinting at a past life as a spiral. But in optical light, they look bland and uninteresting. They rotate like spirals, with the stars in the disk orbiting the center in an organized way. But they don't have the gas needed to form new stars and maintain spiral structure. The leading theory for how lenticular galaxies form is that they're spirals that have been stripped of their gas. This can happen in several ways. Ram pressure stripping in a galaxy cluster, as described earlier. Tidal interactions with other galaxies that pull gas away, or gradual consumption of gas through star formation without any new gas being accreted to replace it. Once the gas is gone, the spiral arms fade because the young blue stars that make them visible die off within a few tens of millions of years, and without new star formation, there's nothing to replace them. What's left is a smooth disk of older stars, a lenticular galaxy. NGC 5866, also known as the Spindle Galaxy, is a beautiful edge-on lenticular located about 44 million light-years away. Seen from the side, it looks like a thin, elongated disk with a bright central bulge and a dark dust lane running along its equator. The dust lane is a remnant of the galaxy's past, as a gas-rich spiral, a small amount of remaining material that hasn't been used up or expelled. The disk itself is smooth and featureless, glowing with the warm light of old red giants and sun-like stars. NGC 5866 is a textbook example of a lenticular, showing all the classic features: disk, bulge, dust lane, and no spiral arms or active star formation. Some lenticular galaxies show more complex structure. NGC 2787, located about 24 million light-years away, has a small bar at its center and weak, tightly wound spiral arms that are only visible in near-infrared light. It also has an active nucleus, a low-luminosity AGN powered by a supermassive black hole that's accreting a trickle of material. The combination of features makes NGC 2787 a transitional object, sitting somewhere between a spiral and a lenticular, and it might represent a galaxy in the process of transforming from one type to the other. Lenticular galaxies are especially common in galaxy clusters, where ram pressure stripping and galaxy interactions are frequent. In the Virgo cluster and the Coma cluster, lenticulars make up a large fraction of the galaxy population, while in the field, regions of space away from clusters, they're much rarer. This environmental dependence supports the idea that lenticulars are created by processes that are more effective in dense environments, like ram pressure stripping and harassment by other galaxies. NGC 524 is a lenticular galaxy about 90 million light-years away that's notable for having a very large, bright bulge and a relatively faint disk, making it look almost like an elliptical galaxy with a thin disk wrapped around it. It also has a prominent ring structure in its inner regions, visible in infrared images, where some star formation is still occurring. The ring might be fed by gas that's been funneled inward by the galaxy's bar, which isn't visible at optical wavelengths, but shows up clearly in infrared. NGC 524 demonstrates that lenticulars aren't completely dead. Some still have reservoirs of gas hidden away, capable of forming stars at a low rate. The Cartwheel Galaxy, discussed earlier as a ring galaxy, might eventually evolve into a lenticular galaxy. After its dramatic encounter with a smaller galaxy, which created the expanding rings of star formation, the cartwheel will eventually settle down as the rings disperse and star formation ceases. What remains will likely be a smooth disk with a bulge, all the hallmarks of a lenticular, with the ring structure only a distant memory preserved in the positions of old stellar populations. Unstable by design, irregular galaxies. Irregular galaxies are the misfits of the galaxy world, lacking the symmetry and structure of spirals and ellipticals. They don't have spiral arms or smooth profiles. Instead, they're chaotic, clumpy collections of stars and gas, often asymmetric and distorted, with no clear center or organizational scheme. They're usually small, comparable to dwarf galaxies, and many of them are undergoing active star formation, their irregular shapes studded with bright blue star clusters and glowing pink nebulae. The Large and Small Magellanic Clouds are the most famous irregular galaxies, visible to the naked eye from the southern hemisphere as two detached pieces of the Milky Way. Both are classified as irregular galaxies, though the Large Magellanic Cloud has hints of spiral structure and might be a disrupted spiral rather than a true irregular. The Small Magellanic Cloud is more chaotic, with no clear structure at all, just a collection of star-forming regions scattered across its disk. Both clouds are being tidally disrupted by their interaction with the Milky Way, which is pulling them apart and stretching them into long streamers of stars and gas. Irregular galaxies often form through gravitational interactions. When two galaxies have a close encounter, even if they don't merge, the tidal forces can distort both galaxies, pulling them into irregular shapes and triggering bursts of star formation. NGC 4449, located about 12 million light-years away, is an irregular galaxy that's been sculpted by interactions with its neighbors. It's forming stars at a high rate, with dozens of bright star clusters scattered across its face, and it has long tidal tails extending outward, evidence of past encounters. NGC 4449 is often called a dwarf irregular, but it's unusually luminous and active for its size, suggesting it's been recently stirred up by gravitational interactions. IC10 is an irregular galaxy in the local group, sitting about 2.2 million light-years away. It's one of the closest starburst galaxies, forming stars at a rate about 10 times higher than the average for galaxies of its size. IC10 is small, faint, and heavily obscured by dust in the plane of the Milky Way, making it difficult to study despite its proximity. Observations in infrared and radio wavelengths reveal a galaxy packed with young star clusters, supernova remnants, and regions of ionized gas, all signs of vigorous star formation. IC10 is thought to be interacting with other members of the local group, which may be driving its high star formation rate. The Magellanic Stream, a long ribbon of neutral hydrogen gas trailing behind the Large and Small Magellanic Clouds, is one of the most prominent irregular structures in the local group. The stream stretches across more than 200 degrees of the sky, wrapping around the Milky Way like a gaseous scarf. It was formed by tidal interactions between the Magellanic Clouds and the Milky Way, which pulled gas out of the clouds and left it behind as they orbit our galaxy. The stream contains about 200 million solar masses of gas, enough to form millions of stars if it can ever condense into clouds dense enough to collapse. Some of the gas in the stream is already falling back into the Milky Way, where it will eventually be incorporated into the disk and recycled into new generations of stars. NGC 1427A is an irregular galaxy falling into the Fornax cluster at high speed, about 600 kilometers per second. The rapid motion through the intracluster medium is compressing the galaxy's gas on its leading edge, triggering intense star formation in a narrow region along one side of the galaxy. The other side of NGC 1427A is relatively quiescent, showing little star formation, creating a striking asymmetry. Over the next few 100 million years, NGC 1427A will be torn apart by tidal forces and ram pressure stripping, its stars scattered through the cluster and its gas stripped away, leaving behind only a faint smear of old stars. The Tadpole Galaxy, mentioned earlier, is a spectacular example of a tidally distorted irregular. Its long tail gives it an unmistakable irregular shape, and observations reveal that star formation is occurring all along the tail, not just in the main body of the galaxy. Some of the star clusters in the tail are massive enough that they might survive as independent objects even after the tail disperses, becoming dwarf galaxies or large globular clusters orbiting in intergalactic space. Irregular galaxies are more common in the distant universe than in the nearby universe. When astronomers look at galaxies billions of light-years away, they find that a much higher fraction are irregular or disturbed compared to today. This makes sense because the early universe was more crowded, and galaxy interactions were much more frequent. Many of today's well-organized spirals and ellipticals were probably irregulars at some point in their past, gradually settling into more regular shapes as they grew and merged with other galaxies. The irregular galaxies we see today might be the last remnants of that chaotic era, small galaxies that haven't yet been accreted by larger ones. The ring galaxies, born from cosmic collisions. Ring galaxies are among the rarest and most striking structures in the universe, representing a unique type of galactic collision where geometry matters as much as mass. Unlike the chaotic mergers that produce ellipticals or the grazing encounters that create tidal tails, ring galaxies form when a small galaxy punches directly through the center of a larger disk galaxy, creating a ripple effect that propagates outward like the waves from a stone dropped in a pond. The result is a brilliant ring of young blue stars surrounding a central core, separated by a gap of relatively empty space. Hoag's object, discovered in 1950 by astronomer Art Hoag, remains the most perfect and mysterious ring galaxy ever found. Located about 600 million light-years away in the constellation Serpens, Hoag's object consists of a nearly circular ring of bright blue stars, approximately 75,000 light-years in diameter, surrounding a spherical yellow core. The gap between the ring and the core is almost completely devoid of stars or visible matter, creating an eerie emptiness. For decades, astronomers debated whether Hoag's object was even a real structure or just a chance alignment of two unrelated galaxies, one behind the other. Spectroscopic observations eventually confirmed that the ring and core are moving together and are at the same distance, proving they're physically connected. The formation mechanism for Hoag's object is still debated. The standard explanation is that a small galaxy passed through the center of a larger disk galaxy, creating a density wave that propagated outward through the disk. As the wave moved, it compressed gas clouds, triggering star formation in a ring that expanded away from the collision point. But there's a problem. There's no sign of the intruder galaxy anywhere nearby. It should still be visible, either inside the ring or having passed out the other side, but searches have found nothing. One possibility is that the intruder was completely destroyed by the collision, torn apart by tidal forces and absorbed into the core. Another idea is that the collision happened so long ago that the intruder has moved far away and is no longer associated with the system. What makes Hoag's object even stranger is what astronomers discovered lurking in the gap between the ring and the core. In deep images taken by the Hubble Space Telescope, a tiny background galaxy is visible in the gap, perfectly positioned between the ring and the core. That background galaxy, which sits about 7 billion light-years away, is itself a ring galaxy, creating a bizarre cosmic coincidence, a ring galaxy seen through the gap of another ring galaxy. The odds of such an alignment are astronomically small, making it one of the most unusual configurations ever photographed. The Cartwheel Galaxy, located about 500 million light-years away in the constellation Sculptor, is a more typical ring galaxy and shows the collision process in action. The Cartwheel has two distinct rings, a bright inner ring and a spectacular outer ring that's actively expanding at about 300,000 kilometers per hour. The outer ring is packed with young star clusters and glowing regions of ionized hydrogen, marking areas where gas has been compressed by the passing density wave. Observations suggest that the collision happened about 200 million years ago, making the Cartwheel a relatively young ring galaxy, still in the early stages of its evolution. Unlike Hoag's object, the Cartwheel still has its intruder galaxies visible. Two small galaxies sit near the edge of the expanding ring, moving away after their violent passage through the Cartwheel's disk. One of them is likely the culprit that created the ring structure, though it's difficult to determine which one was responsible based on their current positions. Computer simulations show that when a small galaxy passes through a larger disk at just the right angle and speed, it creates exactly the kind of expanding ring structure seen in the Cartwheel, confirming that this collision scenario can produce the observed features. The spokes connecting the inner and outer rings of the Cartwheel are another fascinating feature. These spoke-like structures appear to be remnants of the original spiral arms of the galaxy before the collision disrupted them. As the density wave passed through the disk, it distorted the spiral structure, stretching some of the arms radially and creating the appearance of spokes connecting the two rings. Over time, These spokes will continue to evolve and may eventually fade as the galaxy settles into a new equilibrium configuration. A M0644-741, often called Lindsay-Shapley ring, is another spectacular ring galaxy located about 300 million light-years away. It has a single, nearly perfect ring of blue star clusters surrounding a small, faint core. The ring is so symmetrical that it looks almost artificial, like something drawn with a compass rather than formed by natural processes. AM0644-741 is thought to be the result of a nearly head-on collision with a dwarf galaxy, which passed through the center and created the density wave responsible for the ring. The intruder galaxy is no longer visible, either destroyed by the collision or having moved too far away to be detected. Ring galaxies are temporary structures on cosmic timescales. The rings expand outward at hundreds of kilometers per second, and as they do, they gradually dissipate. The star formation triggered by the density wave uses up the available gas, and once the gas is exhausted, the ring begins to fade. The young blue stars that make the ring so prominent live for only a few tens of millions of years, and without new star formation to replace them, the ring gradually reddens and dims. Eventually, perhaps a billion years after the collision, the ring structure will be completely gone, and the galaxy will settle back into a more conventional form, likely an irregular or peculiar galaxy with no obvious signs of its spectacular past. The rarity of ring galaxies tells us something important about galaxy collisions. For a ring to form, the collision must be nearly perpendicular, with the smaller galaxy passing through the center of the larger one at close to a right angle to the disk plane. Most collisions aren't this geometrically perfect. Usually galaxies approach at oblique angles, creating tidal tails, bridges, and other irregular structures instead of rings. The fact that we see any ring galaxies at all is a testament to the vast number of galaxies in the universe and the countless collisions that have occurred over cosmic history. ARPA 147 is a system consisting of two interacting ring galaxies located about 440 million light-years away. The system contains a nearly perfect ring galaxy on the left and a more disturbed spiral galaxy on the right, connected by a bridge of stars and gas. The ring galaxy in ARP 147 formed when the spiral galaxy punched through its disk, creating the density wave that triggered the ring structure. What makes ARP 147 particularly interesting is that the ring contains an unusually high number of ultra-luminous X-ray sources, thought to be intermediate mass black holes or neutron stars, accreting material at extremely high rates. These objects formed from the massive stars born in the Starburst, triggered by the collision, and they're now in the final stages of their violent lives. The luminous infrared galaxies, hidden behind dust. Most galaxies shine brightly at optical wavelengths, the light our eyes can see, but some galaxies are almost invisible in visible light and instead pour most of their energy into the infrared. These luminous infrared galaxies, or LIRGs, and their even more extreme cousins, ultra-luminous infrared galaxies, or ULIRGs, are among the most energetic objects in the universe, radiating more energy than a trillion suns, with more than 90% of that energy coming out in the infrared rather than visible light. The reason these galaxies shine so brightly in the infrared is dust. When stars form, they emit large amounts of ultraviolet and visible light, which heats nearby dust grains to temperatures of a few tens to a few hundred degrees Kelvin. At these temperatures, the dust re-radiates the absorbed energy as infrared light, creating the characteristic infrared glow of dusty star-forming galaxies. In normal galaxies like the Milky Way, only a small fraction of the light is absorbed by dust, so the galaxy remains bright at optical wavelengths. But in LIRGS and ULIRGS, the dust is so thick that it absorbs almost all the ultraviolet and visible light, making the galaxy appear dim or even invisible at optical wavelengths while blazing brilliantly in the infrared. Most luminous infrared galaxies are mergers. When two gas-rich spiral galaxies collide, their gas clouds compress and funnel toward the center of the merging system, triggering intense starbursts and sometimes activating supermassive black holes. The starburst produces enormous numbers of massive stars, which pump out ultraviolet radiation that heats the surrounding dust. The result is a compact, dusty nucleus, radiating tremendous amounts of infrared light. In the most extreme cases, the infrared luminosity exceeds 10 trillion times the luminosity of the Sun, making Ulurgs some of the most luminous galaxies in the universe. ARP 220, located about 250 million light-years away, is the nearest ultra-luminous infrared galaxy and one of the most studied. It's the product of a merger between two large spiral galaxies that began colliding about 700 million years ago. The merger has driven enormous amounts of gas into the central few thousand light-years, where it's forming stars at a rate of several hundred solar masses per year. The core of ARP 220 is completely obscured by dust at optical wavelengths, appearing as a dark, chaotic structure in Hubble images. But observations at infrared and radio wavelengths reveal that the core actually contains two separate nuclei, the remnants of the cores of the two original galaxies, each embedded in a dense cocoon of molecular gas and dust. The two nuclei in ARP 220 are separated by only about 1,200 light-years and are spiraling toward each other, destined to merge into a single nucleus within the next few tens of millions of years. Each nucleus is a compact starburst region, forming stars at rates of hundreds of solar masses per year in a volume less than 300 light-years across. The density of stars in these regions is extraordinary, millions of times higher than in the solar neighborhood, and the supernova rate is correspondingly high, with several supernovas exploding every year. The combined energy output from these supernovae and stellar winds is creating a superwind that's blowing material out of the galaxy at speeds of several thousand kilometers per second, visible as outflows of hot gas detected in X-ray and radio observations. Markarian 231, located about 600 million light-years away, is another Ulurg, notable for being one of the nearest quasars. Unlike ARP 220, where most of the infrared emission comes from star formation, Markarian 231's luminosity is dominated by an actively accreting supermassive black hole. The black hole at the center of Mark 231 has a mass of about 150 million solar masses and is pulling in material at a high rate, releasing energy that outshines the entire starburst. Observations have revealed powerful outflows of gas being driven from the nucleus by the AGN, with velocities reaching 1,000 kilometers per second. These outflows are thought to be blowing away the gas that would otherwise fuel future star formation, gradually quenching the starburst and transforming MRK 231 into a more quiescent galaxy. The importance of luminous infrared galaxies in the history of the universe can't be overstated. When astronomers look at distant galaxies, they find that Lyrigs and Ulurgs were much more common in the past than they are today. During the peak epoch of star formation, about 10 billion years ago, a significant fraction of all stars formed in these dusty, merger-driven starbursts. The infrared luminosity of these galaxies was so high that they contributed as much to the total star formation rate of the universe as all the normal quiescent galaxies combined. Today, the merger rate has dropped as the universe has expanded and galaxies have moved farther apart, making luminous infrared galaxies much rarer in the local universe. The Spitzer Space Telescope and the Herschel Space Observatory revolutionized the study of infrared galaxies by conducting deep surveys at infrared wavelengths, revealing populations of dusty star-forming galaxies that were almost completely invisible at optical wavelengths. These surveys discovered that the universe is filled with infrared bright galaxies at all distances, from the nearby universe out to redshifts greater than 6, when the universe was less than 1 billion years old. Some of these distant infrared galaxies are forming stars at rates of more than 1,000 solar masses per year, creating entire solar systems worth of stars every few days. NGC 6240 is a luminous infrared galaxy about 400 million light-years away that's in the final stages of a major merger. Optical images show a highly disturbed system with long tidal tails extending outward, while infrared observations reveal intense star formation in the overlapping region between the two merging galaxies. X-ray observations made an unexpected discovery. NGC 6240 contains not one but two active supermassive black holes, each accreting material and producing X-rays. The two black holes are separated by only about 3,000 light-years and are orbiting each other as the merger progresses. Eventually, they'll spiral together and merge, producing gravitational waves and creating a single, more massive black hole at the center of the merged galaxy. The antennae galaxies, already discussed for their spectacular tidal tails, are also a luminous infrared galaxy. The collision between the two spirals has driven gas into the overlap region, where it's forming stars at a high rate and heating dust to produce strong infrared emission. Infrared observations reveal more than 1,000 bright star clusters embedded in the dusty clouds, many of them superstar clusters containing millions of young stars packed into regions just a few light-years across. In addition to these well-studied nearby systems, astronomers have uncovered entire classes of extreme infrared galaxies in the early universe that push the limits of what we thought galaxies were capable of. Some of the most dramatic examples are the so-called sub-millimeter galaxies, SMGs. Distant systems discovered not through optical or infrared telescopes at first, but through detectors tuned to longer, sub-millimeter wavelengths. These objects are so heavily obscured by dust that even mid-infrared light struggles to escape. Yet because their dust is heated to temperatures of 30 to 60 Kelvin, the galaxies glow intensely at longer wavelengths. When astronomers traced these emissions back to their origins, they realized that SMGs were forming stars at astonishing rates, sometimes 1,000 to 3,000 solar masses per year, an order of magnitude higher than the most active Learjs in the present-day universe. What makes these early galaxies even more remarkable is how quickly they seem to grow. Observations with ALMA, the Atacama Large Millimeter/Submillimeter Array, show that many SMGs condense hundreds of billions of solar masses of gas into extremely compact regions, sometimes less than 1,000 light-years across. In these environments, gas densities, pressures, and turbulence reach levels rarely seen outside the most extreme galactic mergers. This supports a view that Lyrigs and ULyRGs we see today, like ARP 220 and NGC 6240, are local analogues of processes that were common in the young universe. Back then, galaxies were smaller, more gas-rich, and collided far more frequently. The dusty, infrared bright phase was not an oddity, but a major evolutionary stage. Another key insight from infrared galaxies comes from studying how they evolve after the starburst winds down. Many LIRGs seem to undergo a rapid transformation once their gas is either consumed in star formation or expelled by winds from supernova and active galactic nuclei. The infrared luminosity drops, the dust eventually clears, and the galaxy settles into a more stable form, often resembling an elliptical galaxy with little ongoing star formation. This has led astronomers to propose that dust-enshrouded starbursts are an important pathway for building massive ellipticals, especially those seen dominating galaxy clusters today. In other words, the intensely infrared bright galaxies at high redshift may be the ancestors of the giant red and dead ellipticals we see locally. Another famous example that helps illustrate this transformation is ESO 148-IG002, a merging galaxy pair located about 700 million light-years away. Like ARP 220, it contains two nuclei slowly spiraling inward, each surrounded by thick dust and vigorous star formation. What makes ESO 148 EIG002 particularly interesting is the presence of ordered rotation in the surrounding gas, suggesting that even in the midst of chaos, the system is beginning to form the smooth, rotating structure that will one day become a single, massive galaxy. Infrared and X-ray observations show that both nuclei may harbor growing black holes, and the interactions between these black holes, the surrounding gas, and the starburst all influence how quickly the dust disperses and how fast the galaxy transitions out of its infrared bright phase. Luminous infrared galaxies also play a crucial role in understanding dust itself, how it forms, how it evolves, and how it shapes cosmic history. Dust is produced mainly in supernovae and winds from old stars, but the intense starburst activity in LIRGs accelerates this process. In some systems, the amount of dust present far exceeds what models predicted, suggesting that dust grains might be growing rapidly within dense molecular clouds. This has major implications for our understanding of early galaxies. If dust can form and grow quickly, then the first galaxies in the universe would have become dusty much earlier than expected, helping explain why so many high redshift galaxies discovered by JWST appear heavily obscured. One more well-studied example is IRAS 14348-1447, a spectacular ULIRG about 2 billion light-years away. This system showcases long curving tidal tails stretching tens of thousands of light-years, direct evidence of a large-scale merger. Deep infrared observations show that nearly all of its luminosity comes from two extremely compact starburst regions at its core. The star formation density in these areas is so high that astronomers sometimes refer to them as maximal starbursts, regions that are forming stars as fast as the laws of physics will allow before radiation, turbulence, and stellar winds push back against the collapse of gas. Systems like this help place upper limits on how efficient star formation can be in the universe. As telescopes grow more capable, especially in the far infrared and submillimeter regimes, astronomers continue to uncover new layers to these dusty powerhouses. JWST has already detected smaller, earlier analogues of ULIRGs at redshifts beyond 7, showing that dust-rich starbursts existed when the universe was only a few 100 million years old. Each discovery reinforces the idea that dusty infrared bright galaxies were not just curiosities. They were engines of cosmic evolution, factories where countless stars were forged behind thick curtains of dust. Studying them gives us a clearer picture of how galaxies grow, merge, ignite with starbursts, and eventually settle into the diverse structures we see today. The enormous ellipticals that devoured their neighbors. The largest galaxies in the universe aren't just big, they're monsters, bloated behemoths that grew to their enormous sizes by cannibalizing hundreds or even thousands of smaller galaxies over billions of years. These giant elliptical galaxies, often called CD galaxies, sit at the centers of rich galaxy clusters, where their immense gravity has turned them into cosmic vacuum cleaners, pulling in any galaxy that wanders too close. IC 1101, located about 1.07 billion light-years away at the center of the Abell 2029 galaxy cluster, is often cited as one of the largest known galaxies. With a diameter of roughly 6 million light-years, about 60 times the size of the Milky Way, IC 1101 dwarfs even giant ellipticals like M87. It contains an estimated 100 trillion stars, and its supermassive black hole weighs in at around 40 billion solar masses, one of the most massive black holes ever discovered. The galaxy's enormous size is the result of billions of years of growth through mergers. As smaller galaxies fell into the cluster and were torn apart by IC 1101's gravity, their stars absorbed into the giant's halo. The outer regions of IC 1101 fade so gradually into space that it's hard to say exactly where the galaxy ends and intergalactic space begins. The stellar halo extends for millions of light years, filled with old red stars that were stripped from smaller galaxies during past mergers. These stars now orbit in the combined gravitational field of IC 1101 and the galaxy cluster, creating a diffuse glow called intracluster light that fills the space between galaxies in the cluster core. Observations suggest that as much as 50% of the stars in some rich galaxy clusters are in this intracluster component, untethered to any individual galaxy. A 02261 BCG is another supergiant elliptical that sits at the center of a massive galaxy cluster about 3 billion light-years away. What makes this galaxy particularly unusual is its core, or rather, its lack of one. High-resolution images from the Hubble Space Telescope revealed that a 02261-BCG has a surprisingly flat, low-density center, rather than the bright, compact core that most giant ellipticals possess. This missing core is thought to be the result of a massive black hole merger that occurred in the galaxy's past. When two supermassive black holes merge, they release enormous amounts of energy in the form of gravitational waves. The recoil from this gravitational wave emission can actually kick the merged black hole out of the galaxy center, either ejecting it entirely or causing it to oscillate around the center in a wide orbit, effectively scouring out the core as it moves. The search for the missing black hole in a 02261-BCG has so far been unsuccessful. X-ray observations haven't detected the bright emission that would indicate an actively feeding black hole, and the expected mass of the black hole, tens of billions of solar masses, makes it one of the most massive objects in the universe that's currently unaccounted for. It's possible the black hole is there but dormant, not accreting material, and therefore not producing detectable radiation. Or it might have been ejected from the galaxy entirely, wandering through intergalactic space as a rogue supermassive black hole. NGC 4889, located in the Coma cluster about 300 million light-years away, is another supergiant elliptical with an extraordinary central black hole. The black hole at the heart of NGC 4889 weighs about 21 billion solar masses, and its event horizon, the boundary beyond which nothing can escape, has a diameter of about 130 billion kilometers, roughly 20 times the size of Neptune's orbit. This black hole is currently dormant, not actively accreting significant amounts of material, but observations suggest it was much more active in the past. NGC 4889 shows signs of past AGN activity, including disturbed gas in its center and radio emission from old jets that are no longer being powered. Giant ellipticals grow primarily through dry mergers, collisions between gas-poor galaxies that don't trigger significant star formation. When two elliptical galaxies merge, they simply combine their stellar populations, creating an even larger elliptical without producing many new stars. This is in contrast to wet mergers, collisions between gas-rich spirals that trigger intense starbursts and consume the available gas quickly. Because giant ellipticals have already exhausted their gas supplies through past episodes of star formation, their growth through mergers is relatively gentle and doesn't produce the fireworks of a starburst. M87, the giant elliptical at the center of the Virgo cluster, has a visible jet of plasma shooting from its core, evidence of its active supermassive black hole. The jet extends for at least 5,000 light-years and is visible at optical, radio, and X-ray wavelengths, making it one of the most studied jets in astronomy. The jet is thought to be powered by the rotation of the black hole and its accretion disk, which generates powerful magnetic fields that accelerate particles to nearly the speed of light. The jet punches through the surrounding gas, creating shock waves and cavities that are visible in X-ray images of the hot intracluster medium. The stellar populations of giant ellipticals are almost entirely old and metal-rich, indicating that most of their stars formed more than 10 billion years ago in intense bursts of star formation. Since then, the galaxies have been quietly aging, with very little new star formation to speak of. The red color of these galaxies comes from the dominance of old red giant stars and the absence of young blue stars. Spectroscopic studies reveal that the stars in giant ellipticals are enriched with heavy elements, the products of countless generations of stellar evolution and supernovae that occurred early in the galaxy's history. Messier 60, located about 55 million light-years away in the Virgo cluster, is a giant elliptical that's in the process of merging with a smaller spiral galaxy, NGC 4647. The two galaxies are close together in the sky and appear to be interacting, though the merger is proceeding very slowly due to the low gas content of both galaxies. M60 has a supermassive black hole with a mass of about 4.5 billion solar masses, making it one of the most massive black holes in the nearby universe, relative to the mass of its host galaxy. Beyond these well-known giants, astronomers have identified an entire population of enormous central galaxies that dominate their clusters in ways we're only beginning to understand. Many of these systems exhibit extended envelopes of stars that stretch far beyond what would be expected for ordinary ellipticals, forming faint, ghostly halos millions of light-years across. These halos are built from the accumulated remains of countless galaxies that have been torn apart over cosmic time. As smaller satellites spiral inward, dynamical friction slows them down, causing them to lose orbital energy until they eventually dissolve into the central giant. What's left behind is a diffuse cloud of stars spread across the cluster core, an ongoing record of every galaxy the central monster has consumed. One striking example is ESO 146 IG005, a CD galaxy in a massive cluster nearly 1.7 billion light-years away. Deep optical surveys reveal that its stellar envelope is so extended and faint that it wasn't even recognized as part of a galaxy until astronomers analyzed long-exposure images. The halo is filled with old red giant stars and globular clusters that no longer belong to any individual galaxy. These clusters drift through the cluster like ancient relics, bound only loosely to the colossal gravity well at the center. Observatories studying intracluster light have used systems like this to reconstruct the merger history of galaxy clusters, revealing that some central galaxies have swallowed more than 1,000 smaller systems over their lifetimes. Another fascinating aspect of supergiant ellipticals is their relationship with the hot intracluster medium, the vast reservoir of superheated gas that fills galaxy clusters. Temperatures in this medium can reach tens of millions of degrees, hot enough to emit X-rays detectable by telescopes like Chandra and XMM Newton. The central galaxy plays a key role in shaping this environment. As its black hole accretes material, it releases enormous energy through jets and outflows, carving out bubbles and cavities in the hot gas. These cavities can persist for tens of millions of years, rising through the cluster like giant balloons. In some clusters, researchers have identified multiple generations of bubbles, each marking a past episode of AGN activity. This feedback process helps regulate cooling in the cluster core, preventing the gas from collapsing too quickly and forming new stars. In many ways, the black hole acts as a thermostat for the entire cluster. One of the clearest examples of this feedback in action is found in the Perseus cluster, home to the central giant NGC 1275. Although not as large as IC 1101, NGC 1275 is surrounded by enormous cavities formed by repeated AGN outbursts. These bubbles are among the most dramatic structures in cluster astrophysics, with diameters approaching 50,000 light-years. Shock fronts created by the expanding cavities ripple through the intracluster medium, heating the gas and preventing runaway cooling flows that would otherwise produce rapid star formation. Instead, the central galaxy grows mainly through mergers, following the same dry pattern seen in other giant ellipticals. Some CD galaxies also host vast systems of globular clusters, far more numerous than those found around typical galaxies. For example, the central galaxy in the Arbol 1689 cluster may host more than 100,000 globular clusters, 10 times the number found in the Milky Way. These clusters trace the galaxy's assembly history. Each wave of mergers brings new clusters, which settle into wide, slowly decaying orbits, forming a kind of fossil record of the cluster's formation. The future of these giant galaxies is shaped by the ongoing evolution of clusters themselves. Over billions of years, galaxies within a cluster continue to lose energy through tidal interactions and dynamical friction, gradually spiraling toward the center, where they will eventually be absorbed. In the case of the Virgo cluster, for instance, M87 is likely to consume many of its neighboring galaxies in the distant future, growing even larger and more dominant. Clusters may ultimately evolve into environments where a single supergiant elliptical holds the majority of the cluster's stars, surrounded by only a handful of survivors orbiting at great distances. In the grand scheme of cosmic evolution, these monstrous ellipticals represent the end products of galaxy growth. After endless mergers, countless cannibalized neighbors, and steady black hole feedback shaping their environments, they stand as the universe's largest single structures formed from stars, a testament to billions of years of gravitational competition on the largest scales. Primeval galaxies of the young cosmos. Looking out into space is like looking back in time. Light travels at a finite speed, so when we observe distant galaxies, we're seeing them as they were when their light began its journey toward us, millions or billions of years ago. The most distant galaxies visible today are being seen as they appeared less than 1 billion years after the Big Bang, giving us a window into the early universe when the first galaxies were just beginning to form. The Hubble Ultra Deep Field, An image created by pointing the Hubble Space Telescope at a tiny patch of seemingly empty sky for 11 days revealed thousands of galaxies stretching back to the edge of the observable universe. Some of the galaxies in that image have redshifts greater than 7, meaning their light has been stretched to more than 7 times its original wavelength by the expansion of the universe. These galaxies existed when the universe was less than 800 million years old, in the early stages of what astronomers call the epoch of reionization, when the first stars and galaxies ionized the neutral hydrogen that filled the universe. GNZ 11 held the record for the most distant galaxy known for several years. Located about 13.4 billion light-years away, corresponding to a redshift of 11.09, GNZ 11 is being seen as it appeared just 400 million years after the Big Bang. Despite its youth, GNZ 11 is surprisingly massive and luminous, containing about 1 billion solar masses of stars and forming stars at a rate of about 20 solar masses per year. The galaxy is small, only about 4,000 light-years across, but its brightness and rapid star formation suggest that it was one of the earliest galaxies to form in the universe. The discovery of GNZ 11 and other extremely distant galaxies challenged theories of galaxy formation because they seem too large and too mature for their age. According to models, it takes time for galaxies to assemble from smaller building blocks through mergers and accretion, and there simply wasn't enough time between the Big Bang and 400 million years afterward for such massive galaxies to form. The existence of these early galaxies suggested that either structure formation in the early universe proceeded faster than models predicted, or that the initial conditions, the density fluctuations in the primordial universe, were slightly different than assumed. The James Webb Space Telescope, launched in 2021, has revolutionized the study of early galaxies. With its large mirror and sensitive infrared detectors, JWST can see galaxies that are too distant and too faint for Hubble to detect. Within months of beginning science operations, JWST discovered galaxies at redshifts greater than 13, pushing back the frontier of the observable universe even further. Some of these galaxies appear remarkably mature, with well-developed structures and significant stellar masses, raising new questions about how galaxies formed in the first few 100 million years after the Big Bang. JADE's GSZ 13-0 is one of the most distant galaxies confirmed by JWST, with a redshift of about 13.2, corresponding to a time just 320 million years after the Big Bang. The galaxy is extremely faint and small, containing only a few tens of millions of stars, but it's actively forming new stars and shows signs of ongoing growth. Observations like these are helping astronomers understand how the very first galaxies assembled from the primordial gas that filled the early universe. Early galaxies looked very different from galaxies today. They were smaller, more irregular, and more actively forming stars. Many of them were compact and clumpy, with multiple bright knots of star formation scattered across their disks. The interstellar medium in early galaxies was metal-poor, containing mostly hydrogen and helium, with only trace amounts of heavier elements, because there hadn't been enough time for many generations of stars to produce and distribute metals through supernovae. As a result, the stars that formed in early galaxies were different from stars today, often more massive and hotter due to the low metallicity of the gas. The epoch of reionization, which occurred between about 400 million and 1 billion years after the Big Bang, was a crucial period in cosmic history when the first stars and galaxies ionized the neutral hydrogen that pervaded the universe. Before reionization, the universe was opaque to ultraviolet light because neutral hydrogen absorbs UV photons very efficiently. Once stars began forming in large numbers, their ultraviolet radiation ionized the surrounding hydrogen, creating bubbles of ionized gas that expanded and eventually overlapped, ionizing the entire universe. By about 1 billion years after the Big Bang, reionization was complete, and the universe became transparent to ultraviolet light. Lyman alpha emitters are a class of galaxies that are particularly useful for studying the early universe. These galaxies emit strong Lyman alpha emission, a specific wavelength of ultraviolet light produced when electrons in hydrogen atoms transition from the first excited state to the ground state. Lyman alpha emission is extremely bright in young, actively star-forming galaxies, making them easy to detect even at high redshifts. Surveys for Lyman alpha emitters have revealed thousands of galaxies at redshifts between 2 and 7, providing a census of star-forming galaxies during the peak epoch of galaxy formation. The Lyman alpha forest is another tool for studying the early universe. When light from a distant quasar passes through the intergalactic medium on its way to Earth, it encounters clouds of neutral hydrogen that absorb light at the Lyman alpha wavelength. Each cloud creates an absorption line in the quasar's spectrum, and because the clouds are at different distances and therefore different redshifts, the absorption lines pile up to create a forest of lines blueward of the quasar's own Lyman alpha emission. By analyzing the Lyman alpha forest, astronomers can map out the distribution of neutral hydrogen in the intergalactic medium and study how it evolved over cosmic time. Submillimeter galaxies are another important population of galaxies in the early universe. These are distant, dusty galaxies that emit most of their light in the far infrared and submillimeter wavelengths. Like local ULIRGS, submillimeter galaxies are undergoing intense starbursts, forming stars at rates of hundreds or even thousands of solar masses per year. Many submillimeter galaxies are thought to be the progenitors of today's giant elliptical galaxies, building up their stellar masses through brief but intense periods of star formation in the first few billion years after the Big Bang. The polar ring galaxies with perpendicular orbits. Among the most peculiar types of galaxies are polar ring galaxies, objects where a ring of stars, gas, and dust orbits perpendicular to the main disk or body of the galaxy. These structures look impossible, as if someone assembled a galaxy incorrectly, stacking two components at right angles. Yet they're real, and they provide unique insights into galaxy formation, dark matter distribution, and the complex dynamics of gravitational interactions. NGC 4650A, located about 130 million light-years away, is the prototypical polar ring galaxy. It consists of a central lenticular galaxy, a smooth, disc-like structure with no spiral arms, surrounded by a ring of material that's tilted almost exactly 90 degrees relative to the central galaxy's disk. The polar ring is full of gas and actively forming stars, glowing with the blue light of young star clusters and the pink hues of ionized hydrogen nebulae. The central lenticular component, in contrast, is red and quiescent, dominated by old stars with little ongoing star formation. The most widely accepted explanation for polar ring galaxies is that they form through the accretion of material from a smaller galaxy during a merger or close encounter. If a gas-rich dwarf galaxy approaches at the right angle and speed, tidal forces can strip gas and stars from the dwarf and deposit them in an orbit perpendicular to the main galaxy's disk. Over time, this accreted material settles into a stable polar ring, while the dwarf galaxy itself may be completely destroyed or reduced to a small remnant. Computer simulations show that this scenario can produce structures that look remarkably similar to observed polar ring galaxies, supporting the merger hypothesis. What makes polar ring galaxies scientifically valuable is that they allow astronomers to measure the shape of the dark matter halo. In most galaxies, we can only measure the orbital velocities of stars and gas in the main disk, which gives us information about the mass distribution in the plane of the disk. But polar rings orbit perpendicular to the disk, so by measuring their rotation speeds, we can determine how much mass exists in that direction. If dark matter halos are spherical, the rotation speeds should be similar in all directions. If they're flattened or elongated, the rotation speeds in different directions will differ. Studies of polar ring galaxies suggest that dark matter halos are generally close to spherical or only slightly flattened, consistent with predictions from computer simulations of structure formation. NGC 2685, nicknamed the Helix Galaxy, is another well-known polar ring system located about 50 million light-years away. Unlike NGC 4650A, which has a simple central disk and polar ring, NGC 2685 has a more complex structure with multiple components at different angles. The central galaxy is a lenticular, but it's surrounded by several nested rings and shells of material, some tilted at intermediate angles between the disk plane and the polar direction. The complexity suggests that NGC 2685 has undergone multiple interactions or mergers, each depositing material in a different orbit. The polar ring in NGC 4650A rotates at speeds that indicate a large amount of mass is present, far more than can be accounted for by the visible stars and gas. This is further evidence for dark matter. The polar ring is orbiting in the combined gravitational field of the central galaxy's dark matter halo, and the rotation speeds tell us how massive that halo is. Measurements suggest that the dark matter halo of NGC 4650A extends well beyond the visible galaxy, out to distances of at least 200,000 light-years, and that it contains about 10 times more mass than all the visible matter in the galaxy. Centaurus A, the giant elliptical galaxy mentioned earlier, has features that resemble a polar ring. The dark dust lane that crosses its center is thought to be the remnant of a spiral galaxy that Centaurus A recently absorbed, and the dust lane is tilted at a significant angle relative to the main body of the elliptical. While not a classic polar ring system, Centaurus A demonstrates that material accreted from other galaxies can end up in orbits that are tilted or perpendicular to the main galaxy's structure. UGC 7576 is a faint polar ring galaxy about 470 million light-years away. It's less well studied than NGC 4650A, but observations show that it has a clear ring of gas and stars orbiting perpendicular to a central lenticular component. The ring contains regions of active star formation, indicating that it's composed of relatively young material, likely accreted within the last billion years. The faintness and distance of UGC 7576 make it challenging to study in detail, but it represents the typical case. Most polar ring galaxies are distant and faint, making them difficult to detect and characterize. Only about 100 polar ring galaxy candidates are known, making them one of the rarest types of galaxies. The scarcity suggests that the conditions needed to form a polar ring are quite specific. The merger or interaction must occur at just the right angle and with the right mass ratio to deposit material in a perpendicular orbit without disrupting the central galaxy too severely. If the encounter is too violent or occurs at the wrong angle, the result will be a more chaotic merger or a tidal tail rather than a neat polar ring. Some polar ring candidates are ambiguous, and it's not always clear whether they're genuine polar rings or just chance alignments of unrelated galaxies. Deep imaging and spectroscopy are needed to confirm that the ring and central galaxy are physically associated and moving together, rather than just appearing close together in projection on the sky. As a result, the number of confirmed polar ring galaxies is smaller than the number of candidates, and new discoveries continue to add to the catalogue. The dwarf spheroidal galaxies dominated by dark matter. Dwarf spheroidal galaxies are some of the faintest and least luminous objects in the universe that still qualify as galaxies. They contain anywhere from a few thousand to a few million stars spread over volumes thousands of light-years across, giving them such low surface brightnesses that they're extremely difficult to detect. Yet despite their faintness, dwarf spheroidals are scientifically important because they're the most dark matter-dominated objects known, with mass-to-light ratios reaching hundreds or even thousands in some cases. The Sculptor dwarf spheroidal galaxy, located about 290,000 light-years away, is one of the nearest and brightest dwarf spheroidals. It's a satellite of the Milky Way, orbiting our galaxy in the outer halo. Sculptor contains only about 3 million stars, making it roughly 1 million times less luminous than the Milky Way, but measurements of its internal stellar velocities reveal that it contains far more mass than can be accounted for by the visible stars alone. The velocity dispersion, the spread in velocities of stars moving randomly within the galaxy, is high enough to require a total mass about 10 times greater than the stellar mass, implying that Sculptor is embedded in a massive dark matter halo. Dwarf spheroidals are completely devoid of gas and show no signs of ongoing star formation. Their stellar populations are old, with most stars having formed more than 10 billion years ago, and their red color reflects the dominance of old red giants. The lack of gas is somewhat mysterious because these galaxies are so small and have such weak gravity that supernova explosions should have been able to blow away their gas early in their history. Alternatively, tidal interactions with larger galaxies like the Milky Way could have stripped away the gas, or the gas might have been removed by ram pressure stripping as the dwarf spheroidal moved through the hot gas in the Milky Way's halo. The Draco dwarf spheroidal galaxy, located about 260,000 light-years away, is another Milky Way satellite. It's even fainter than Sculptor, containing only about 300,000 stars, and it's so diffuse that it has one of the lowest surface brightnesses of any known galaxy. Draco's velocity dispersion is surprisingly high for such a small galaxy, indicating a mass-to-light ratio of about 340, one of the highest ever measured. This means that for every solar mass of visible stars in Draco, there are 340 solar masses of dark matter, making it one of the most dark matter-dominated galaxies known. The extreme dark matter dominance of dwarf spheroidals makes them prime targets for dark matter searches. If dark matter consists of particles that can annihilate or decay, producing gamma rays or other detectable signals, then dwarf spheroidals should be among the brightest sources of such signals because they're so dominated by dark matter and relatively nearby. Astronomers have used gamma-ray telescopes to observe dozens of dwarf spheroidals looking for faint glows that could indicate dark matter annihilation. So far, these searches have found no convincing signals, but they've placed important constraints on the properties of dark matter particles, ruling out some theoretical models and narrowing down the possibilities. Segway 1, discovered in 2006 in data from the Sloan Digital Sky Survey, is one of the faintest galaxies ever discovered. It contains only about 1,000 stars and has a luminosity just 300 times that of the Sun, making it barely brighter than some globular clusters. Yet velocity measurements indicate that Segway 1 has a mass-to-light ratio of about 3,400, even higher than Draco. This extraordinary ratio suggests that Segway 1 is almost entirely dark matter with just a tiny sprinkling of visible stars, like the tip of an iceberg barely poking above the water. The existence of ultra-faint dwarf spheroidals, like Segway 1, was predicted by models of structure formation in a universe dominated by cold dark matter. According to these models, dark matter clumps together on all scales, forming halos ranging from the size of galaxy clusters down to much smaller scales. The smallest dark matter halos should host the faintest galaxies, objects with so few stars that they're almost impossible to detect. The discovery of ultra-faint dwarfs confirmed this prediction and provided strong support for the cold dark matter paradigm. However, there's a problem known as the missing satellites problem. Simulations of Milky Way-sized dark matter halos predict that there should be hundreds or even thousands of small dark matter subhalos orbiting within the halo, each potentially capable of hosting a dwarf galaxy. But we only see a few dozen dwarf satellites around the Milky Way, even after deep surveys have revealed the ultra-faint population. Either the simulations are overestimating the number of subhalos, or most subhalos are completely dark, with no stars at all. Several solutions have been proposed, including the idea that small halos had their gas blown away by the ultraviolet radiation from the first stars and never formed any stars, or that the process of star formation is so inefficient in small halos that most of them remain dark. Willman 1 is another ultra-faint dwarf discovered in 2004. It's so faint and so diffuse that there was initially debate about whether it was even a galaxy or just a distant globular cluster. Spectroscopic observations eventually confirmed that it's a dwarf spheroidal galaxy with a velocity dispersion indicating a significant dark matter content. Willman 1 contains only a few hundred stars and has a total luminosity about 1,000 times that of the Sun, making it one of the intrinsically faintest galaxies known. The discovery of numerous ultra-faint dwarfs in the last 2 decades has been enabled by large digital sky surveys like the Sloan Digital Sky Survey, and more recently by surveys conducted with telescopes like the Dark Energy Camera and the Hyper-Suprime Cam. These surveys image enormous areas of the sky to great depth, allowing astronomers to search for the faint, extended structures that characterize dwarf galaxies. By looking for regions with a slight overdensity of stars compared to the background, algorithms can identify candidate dwarf galaxies, which are then followed up with spectroscopy to confirm their nature. Tucana 3 is a dwarf spheroidal galaxy located about 75,000 light-years away, making it one of the closest known ultra-faint dwarfs. What makes Tucana 3 particularly interesting is that it appears to be in the process of being tidally disrupted by the Milky Way. Observations show a stream of stars extending from the main body of the galaxy, evidence that tidal forces are pulling stars away. Over the next few 100 million years, Tucana 3 will likely be completely torn apart, its stars scattered through the Milky Way's halo. The discovery of tidal streams from ultra-faint dwarfs provides direct evidence that the Milky Way is still actively accreting smaller galaxies, a process that's ongoing even today. Void galaxies in the cosmic web. The universe is not uniformly filled with galaxies. Instead, galaxies are arranged in a vast cosmic web, concentrated in filaments and clusters, with enormous empty regions in between. These voids are the largest structures in the universe, vast expanses of space hundreds of millions of light-years across that contain very few galaxies. While voids aren't completely empty, the galaxies within them are much more isolated than those in denser regions, and they evolve differently as a result. The Buttes void, discovered in 1981, is one of the largest and most famous voids in the nearby universe. It's roughly spherical, about 330 million light-years in diameter, and sits about 700 million light-years from Earth. When it was first discovered, surveys found only 60 galaxies in a region where tens of thousands would be expected based on the average density of the universe. This made the Buttes void seem almost completely empty, earning it the nickname the Great Nothing. Later, more sensitive surveys found additional galaxies, bringing the total to a few thousand. But the void remains dramatically underdense compared to typical regions of space. Galaxies in voids tend to be different from galaxies in denser environments. Void galaxies are more likely to be spirals or irregulars, with ongoing star formation and plentiful gas. This is because void galaxies have experienced fewer interactions and mergers than galaxies in clusters or filaments, allowing them to retain their gas and continue forming stars over long timescales. They're also more likely to be small, with fewer massive galaxies in voids compared to the general population. This makes sense because massive galaxies typically grow through mergers, and mergers are less common in the sparse environment of a void. MCG plus 01-02-015 is a spiral galaxy located in the Buttes void, one of the few relatively bright galaxies in that enormous empty region. It's an ordinary-looking spiral with active star formation, similar to many galaxies in more typical environments, but its isolation is extreme. The nearest other galaxy to MCG plus 01-02-015 is tens of millions of light-years away, making it one of the most isolated galaxies known. Studies of void galaxies like MCG plus 01-02-015 help astronomers understand how galaxies evolve in the absence of interactions and external influences. Voids are expanding faster than the average expansion of the universe. This might seem paradoxical, but it's a natural consequence of gravity. In regions with higher than average density, gravity slows the expansion, pulling matter together and causing filaments and clusters to form. In regions with lower than average density, there's less matter and therefore less gravity, allowing the expansion to proceed faster. As a result, voids grow over time, pushing galaxies outward toward the surrounding filaments and making the cosmic web more pronounced. This process is ongoing, and simulations predict that voids will continue to grow and merge, eventually creating even larger empty regions. The formation of voids is intimately connected to the growth of structure in the universe. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny density fluctuations. Over time, gravity amplified these fluctuations. Regions that were slightly denser than average attracted more matter and became denser still, while regions that were slightly less dense had matter flow out of them, becoming even more underdense. This process created the cosmic web we see today, with filaments and clusters marking the dense regions and voids marking the underdense ones. KK246 is a dwarf irregular galaxy located in a void, one of many small galaxies that have been discovered in these sparse regions. Despite the low density of voids, they're not completely devoid of galaxies. Instead, they contain a population of mostly small, faint galaxies that are difficult to detect but are present in significant numbers. Surveys targeting void regions have revealed that while the overall density of galaxies is low, there are still thousands of galaxies lurking in these enormous empty spaces, just spread out over much larger volumes than in typical regions. The local void is a smaller void in our cosmic neighborhood, sitting about 200 million light-years from the Milky Way. While not as large or as empty as the Buta's void, the local void is significant because it's close enough that individual galaxies within it can be studied in detail. The local void is bounded by several large structures, including the local sheet, a flat distribution of galaxies that includes the Milky Way and Andromeda and the Virgo cluster. The motion of our local group of galaxies is influenced by the gravitational pull of these surrounding structures, as well as by the repulsive effect of the void, which pushes outward as it expands. Void galaxies provide a control sample for studying galaxy evolution. Because they've experienced minimal environmental effects like ram pressure stripping, tidal interactions, or harassment from other galaxies, void galaxies show us what happens to galaxies in isolation. By comparing void galaxies to galaxies in clusters or groups, astronomers can isolate the effects of environment on galaxy properties like star formation rate, gas content, and morphology. These comparisons have shown that environment plays a major role in determining how galaxies evolve, with dense environments tending to shut down star formation and transform spirals into lenticulars or ellipticals, while void environments allow galaxies to continue forming stars and retain their gas. Another remarkable feature of cosmic voids is the presence of void walls, thin, faint surfaces where matter has been gently pushed outward during billions of years of expansion. These walls can sometimes host long, delicate chains of dwarf galaxies that formed from leftover gas that never made it into the denser filaments. Compared to the bright, richly populated filaments of the cosmic web, these walls are extremely subtle structures, often invisible except in deep surveys that map galaxy positions over enormous volumes. Simulations suggest that the matter within void walls moves almost coherently, drifting outward as the void interior expands, creating a quiet, steady flow of galaxies toward the edges. One of the best studied examples of this process is seen in the Draco void and its surrounding structures. Although not as large as the Buta's void, the Draco void contains a number of extremely isolated galaxies whose motions illustrate how void dynamics influence galaxy trajectories. These galaxies are not simply sitting still in empty space, they're being slowly pushed outward by the void's expansion, a subtle effect that accumulates over billions of years and can produce measurable, peculiar velocities. Observations of these motions give cosmologists valuable insights into the distribution of dark matter, because the rate of void expansion is sensitive to the underlying gravitational landscape. Some void galaxies exhibit unusual characteristics that make them stand out compared to galaxies in denser regions. For example, a number of void galaxies appear to have higher specific star formation rates than typical spirals. This may be because their gas reservoirs have never been stripped or consumed by interactions, leaving large supplies of cold hydrogen available for slow, continuous star formation. In some cases, these galaxies appear almost pristine, containing gas with very low metallicity, evidence that their stars have formed gradually over time without the enrichment typically introduced by mergers or interactions. An excellent example is SDSSJ 1352-0031, a dwarf galaxy deep within a void that shows unusually low metal content for its age. This has led astronomers to speculate that some void galaxies may continue to form stars from nearly primordial gas, material that has remained untouched since the early universe. Although such cases are rare, they demonstrate that voids can preserve conditions similar to those that were common billions of years ago, offering a unique laboratory for studying early galaxy evolution in the present-day universe. Another surprising discovery is the existence of large-scale filaments inside voids, albeit faint and sparsely populated. These mini-filaments are thought to be the remnants of weak density fluctuations that never grew into full cosmic web structures. They often contain chains of dwarf galaxies separated by tens of millions of light-years. Compared to the thick, complex filaments between clusters, these mini-filaments are thin, fragile, and sparsely built, but they hold valuable clues about how structure forms on the smallest cosmic scales. The boundaries of voids are also important for understanding cosmic flows. The Milky Way, for example, is located near the edge of the local void, and measurements of galaxy motions show that our entire local group is slowly drifting away from the void's interior and toward denser regions like the Virgo cluster and the Great Attractor. This motion is a combination of gravitational attraction from massive structures and the relative push of the expanding void. The effect isn't like a physical force pushing on galaxies, but rather a difference in gravitational density. Galaxies move toward regions with more matter, leaving underdense regions behind. As the universe continues to age, voids will become increasingly dominant. The cosmic web will grow more pronounced, with dense regions becoming even denser and empty regions becoming even emptier. In the distant future, astronomers predict that voids may merge into enormous supervoids, spanning more than 1 billion light-years, leaving behind isolated clusters or groups surrounded by vast stretches of nearly empty space. One of the largest currently known supervoids is the Eridanus supervoid, which stretches for hundreds of millions of light-years and has been studied as a possible explanation for the CMB cold spot. Although its exact influence is still debated, the Eridanus supervoid demonstrates that voids can have significant effects on the cosmic microwave background through the integrated Sachs-Wolf effect, subtly altering the energy of photons as they travel through underdense regions. The galaxies at the edge of detection. At the farthest reaches of the observable universe, billions of light-years away, lie galaxies so distant and so faint that they push the limits of even our most powerful telescopes. These galaxies are being seen as they appeared when the universe was young, often less than 1 billion years old, and studying them reveals how galaxies formed and evolved in the early universe. But detecting these distant galaxies is extraordinarily difficult, requiring cutting-edge technology and innovative observing strategies. The James Webb Space Telescope has transformed the study of distant galaxies. Unlike Hubble, which observes primarily at optical and ultraviolet wavelengths, JWST is optimized for infrared light. This is crucial for studying distant galaxies because the expansion of the universe stretches their light to longer wavelengths, shifting what was originally ultraviolet and optical light into the infrared. A galaxy at redshift 10, for example, has its light stretched by a factor of 11, so a UV photon emitted at 200 nanometers arrives at Earth as an infrared photon at 2,200 nanometers. Only an infrared telescope like JWST can detect these galaxies. Within months of beginning science operations in 2022, JWST discovered numerous galaxies at redshifts greater than 10, seeing them as they appeared less than 500 million years after the Big Bang. Some of these galaxies are surprisingly bright and massive for their age, challenging theories of how quickly galaxies can assemble in the early universe. JADE's GS-Z14-0, discovered in the JWST Advanced Deep Extragalactic Survey, has a redshift of approximately 14.32, making it one of the most distant galaxies ever confirmed. At that redshift, the galaxy is being seen just 280 million years after the Big Bang, during the earliest stages of galaxy formation. Gravitational lensing is another powerful tool for studying distant galaxies. When a massive galaxy cluster sits between us and a more distant background galaxy, the cluster's gravity bends and amplifies the light from the background galaxy, acting like a cosmic magnifying glass. This gravitational lens effect can boost the brightness of distant galaxies by factors of 10, 100, or even more, making them visible when they would otherwise be too faint to detect. The downside is that the lensing distorts the image, stretching the background galaxy into arcs or multiple images, but astronomers can model the lensing and reconstruct what the galaxy actually looks like. The galaxy MAX 0647-JD was one of the most distant galaxies known before JWST, discovered in 2012 using Hubble images of the galaxy cluster MAX J 0647. The background galaxy is being lensed by the cluster, and the gravitational magnification makes it bright enough to be detected despite its enormous distance. MAX 0647-JD has a redshift of about 10.7, corresponding to a time about 420 million years after the Big Bang. Follow-up observations with JWST have revealed more details about this galaxy's structure and star formation properties, showing that it's actively forming stars and is more complex than it initially appeared. Lyman break galaxies are a class of distant star-forming galaxies that can be identified by their distinctive colors. The Lyman break refers to a sharp drop in the galaxy's brightness at wavelengths blueward of 912 angstroms in the rest frame, caused by absorption of UV light by neutral hydrogen in the galaxy and along the line of sight. Because of the cosmological redshift, this feature moves to longer wavelengths for distant galaxies, making it possible to identify them using multiband imaging. Surveys for Lyman break galaxies have found tens of thousands of examples at redshifts between 2 and 7, providing a census of star-forming galaxies during the peak epoch of cosmic star formation. The colors of distant galaxies tell us about their stellar populations and star formation histories. Young galaxies actively forming stars appear blue because hot, massive stars emit most of their light at blue and ultraviolet wavelengths. As galaxies age and star formation declines, they become redder as the massive blue stars die off, and the remaining population is dominated by cooler, longer-lived red and yellow stars. By measuring the colors and brightnesses of distant galaxies at multiple wavelengths, astronomers can estimate their ages, stellar masses, and star formation rates, building up a picture of how galaxies grow and change over cosmic time. Some of the faintest galaxies at the edge of detection are so small and faint that they're barely resolved even in deep Hubble and JWST images, appearing as just a few pixels of slightly enhanced brightness against the sky background. These galaxies might contain only a few million or tens of millions of stars, making them the distant ancestors of today's dwarf galaxies. Studying them is challenging because their faintness makes spectroscopy, the key tool for measuring redshifts and other properties, extremely difficult. Astronomers often have to rely on photometric redshifts, estimates based on the galaxy's colors rather than detailed spectra, which are less precise but still useful for statistical studies. The Hubble Frontier Fields program used gravitational lensing to study some of the faintest distant galaxies ever detected. By targeting 6 massive galaxy clusters known to be strong lenses, the program obtained extremely deep images of the background universe, revealing hundreds of lensed galaxies at high redshifts. Some of these galaxies are so faint that they would be completely invisible without the magnification provided by the cluster lens. Analysis of the Frontier Fields data has shown that faint galaxies were extremely abundant in the early universe, possibly contributing as much to the total star formation as brighter, more massive galaxies. Starburst phenomena in dwarf galaxies. Blue compact dwarf galaxies are small, irregularly shaped galaxies undergoing intense bursts of star formation. Despite their small size, typically containing only a few billion stars or less, they're forming stars at rates comparable to much larger galaxies, creating brilliant blue regions packed with young, massive stars. These galaxies are laboratories for understanding star formation in extreme conditions, and may be similar to the building blocks that assembled to form larger galaxies in the early universe. IZW18 is one of the most famous blue compact dwarfs, located about 59 million light-years away. For decades, it held the record as the most metal-poor galaxy known, with an oxygen abundance only about 3% that of the Sun. This low metallicity suggests that IZW18 has undergone very few generations of star formation, with most of its stars being relatively young. Observations show that the galaxy has at least 2 major star-forming regions, each containing thousands of hot, massive stars that are ionizing the surrounding gas and creating the galaxy's characteristic blue color. The extreme metal poverty of IZW18 raised an interesting question. Could it be a newly formed galaxy, a primordial object that's forming stars for the first time? This would make it a local example of the kinds of galaxies that existed in the early universe. However, deep imaging with the Hubble Space Telescope revealed a faint, underlying population of older red stars, indicating that IZW18 has been forming stars for at least a few billion years, though at a very low average rate. The current intense starburst is just the latest episode in a complex history of on and off star formation. NGC 1569 is another blue compact dwarf, located about 11 million light-years away in the constellation Camelopardalis. It's undergoing a powerful starburst that started about 25 million years ago and is still ongoing. The starburst has produced several superstar clusters, compact regions containing hundreds of thousands or millions of young stars, packed into volumes just a few light-years across. These superstar clusters are so dense and so bright that they're visible as distinct objects in Hubble images, each one shining with the light of hundreds of thousands of suns. The starburst in NGC 1569 has also produced a powerful superwind, driven by the combined energy of stellar winds and supernova explosions from thousands of massive stars. The superwind is blowing hot gas out of the galaxy at speeds of several hundred kilometers per second, creating a glowing halo visible in X-ray images. The wind is carrying away not just gas, but also the heavy elements produced by the starburst, enriching the intergalactic medium and possibly preventing future star formation by removing the raw material needed to make new stars. Blue compact dwarfs are thought to be triggered by interactions with other galaxies or by gas accretion. When a small galaxy passes near a larger one, tidal forces can compress its gas, triggering a burst of star formation. Alternatively, if a dwarf galaxy accretes a fresh supply of gas from the intergalactic medium, that gas can fuel a starburst. In either case, the starburst is temporary, lasting only a few tens of millions of years before the available gas is exhausted or expelled by stellar feedback. Harrow 11 is a blue compact dwarf about 300 million light-years away that's notable for being one of the most prolific producers of ionizing radiation in the nearby universe. The galaxy is forming stars at such a high rate that it's creating enormous numbers of hot, massive stars, which pump out ultraviolet radiation that ionizes the surrounding gas. Some of this ionizing radiation is escaping the galaxy entirely, leaking out into intergalactic space, making Harrow 11 a local analog for the galaxies that reionize the universe in its early history. The star formation in blue compact dwarfs is not distributed uniformly across the galaxy. Instead, it's concentrated in one or a few bright knots, creating a lumpy, asymmetric appearance. This clumpiness is a hallmark of star formation in low-mass galaxies, where the gas is not smoothly distributed, but instead concentrated in dense clouds that can collapse to form stars. The resulting star clusters are often massive and compact, similar to the globular clusters that orbit large galaxies, and some of them may survive for billions of years, becoming the globular clusters of the future. The peculiar galaxies that defy classification. Not all galaxies fit neatly into the standard categories of spirals, ellipticals, and irregulars. Some galaxies are so strange, so unlike anything else, that they've earned the designation peculiar, a catch-all category for objects that don't fit the normal classification schemes. Peculiar galaxies often show signs of recent interactions or mergers, with distorted shapes, tidal tails, and other features that mark them as works in progress, caught in the act of transforming from one type to another. ARP 273, located about 300 million light-years away, is a stunning pair of interacting galaxies. The larger galaxy, UGC 1810, has been dramatically distorted by a close encounter with its smaller companion, UGC 1813. The interaction has pulled out a long tidal tail from UGC 1810 and has created a striking rose-like pattern in its spiral arms. The outer spiral arm has been stretched and pulled upward by the gravitational interaction, giving the galaxy a distinctive lopsided appearance. The smaller companion has also been distorted, stretched into an elongated shape by tidal forces. The Porpoise galaxy, officially known as NGC 2936, is a spectacular example of a spiral galaxy being tidally disrupted by an elliptical companion. The spiral has been stretched and twisted by the interaction, creating a structure that looks remarkably like a porpoise or penguin with a head and beak, formed by tidal forces pulling stars and gas outward. The elliptical companion, NGC 2937, sits nearby, relatively undisturbed because its stars are more tightly bound by gravity and less susceptible to tidal disruption. Over time, the two galaxies will merge, creating a larger elliptical galaxy and erasing the peculiar structure we see today. Mayall's object, also known as ARP 148, is the result of a collision between two galaxies that occurred about 40 million years ago. The collision was so violent that it completely disrupted both galaxies, creating a bizarre structure consisting of a ring of blue star clusters connected by a long tail to a more diffuse region. The ring formed when one galaxy punched through the disk of the other, creating a density wave that expanded outward and triggered intense star formation. The tail contains older stars pulled out of the galaxies by tidal forces during the collision. Mayall's object is a transitional structure, destined to evolve into a more conventional galaxy as the ring disperses and the system settles down. Centaurus A's dust lane, mentioned earlier, makes it a peculiar elliptical. The thick band of dust cutting across its center is completely out of place in an elliptical galaxy, which shouldn't have any dust or gas. The dust lane is the remnant of a spiral galaxy that Centaurus A accreted, and it's still visible even though the merger likely happened tens of millions of years ago. The presence of the dust lane, combined with the galaxy's active nucleus and powerful radio jets, makes Centaurus A one of the most peculiar galaxies in the nearby universe. Haugh's object, already discussed as a ring galaxy, is peculiar even among ring galaxies because of its near-perfect symmetry and the complete absence of any visible intruder galaxy. Most ring galaxies show clear signs of the collision that created them, but Haugh's object looks suspiciously perfect, almost as if it were artificially constructed. Some astronomers have proposed alternative explanations for its structure, including the idea that it might be a gravitational lens system where a distant blue ring-shaped galaxy is lensed by a foreground elliptical. But this explanation has been ruled out by spectroscopic observations, showing that the ring and core are at the same distance. The Atoms for Peace galaxy, officially designated NGC 7252, is a peculiar elliptical formed by the merger of two spiral galaxies. The merger occurred relatively recently, about 1 billion years ago, and the galaxy still shows signs of the collision, including faint tidal tails and a disturbed structure. Deep images reveal loops and shells of stars surrounding the galaxy, created by the complex gravitational interactions during the merger. NGC 7252 is an example of how mergers transform spirals into ellipticals, and it's caught at a transitional stage where the merger is complete, but the galaxy hasn't yet fully relaxed into a smooth elliptical shape. Messier 82's superwind, described earlier, makes it a peculiar starburst galaxy. The intense star formation in its core has created a visible outflow of hot gas, extending thousands of light years above and below the galactic plane, creating filaments and glowing regions that are visible in optical, infrared, and X-ray images. The superwind is so powerful that it's blowing material completely out of the galaxy, enriching the surrounding intergalactic medium with heavy elements and potentially shutting down future star formation by removing the gas needed to make new stars. Peculiar galaxies are fascinating not only because of their strange appearances, but also because they tell the story of galactic evolution in action. Unlike the standard spirals and ellipticals, which have long since settled into stable configurations, peculiar galaxies often occupy transitional stages. They reveal what happens when gravity and collisions shape the cosmos on grand scales. By studying them, astronomers gain insight into how galaxies form, grow, and sometimes violently rearrange their stars, gas, and dust. One particularly striking example is NGC 6745, sometimes called the Bird Galaxy due to its unusual shape. This galaxy is actually the result of a high-speed collision between two galaxies, one much smaller than the other. The smaller galaxy has been almost entirely shredded, leaving behind streams of stars and gas that wrap around the larger galaxy like feathers in a bird's plumage. The main body of NGC 6745 appears irregular, with knots of intense star formation scattered throughout. These starburst regions are ignited as the gas clouds collide and compress, creating conditions where new stars form at rates far above what we see in isolated spiral galaxies. Observations in optical, infrared, and radio wavelengths show that the collision has triggered both intense star formation and the growth of a central supermassive black hole, hinting at the complex interplay between mergers and black hole evolution. Another remarkable system is NGC 4038 and NGC 4039, collectively known as the antennae galaxies. This pair of interacting spirals has been locked in a gravitational dance for hundreds of millions of years. The tidal forces between the two galaxies have pulled out enormous, elongated streams of stars and gas, forming the iconic antenna-like tails that give the system its name. These tails are not mere decorations, they are active sites of star formation containing clusters of young, massive stars forming within dense molecular clouds. The antennae galaxies provide a vivid example of how collisions can simultaneously destroy and create, disrupting the original galaxies while giving rise to new stars, star clusters, and even dwarf galaxies in the tidal tails. Observing these systems in detail helps astronomers understand how mergers drive the hierarchical growth of galaxies throughout cosmic history. NGC 4650A is another peculiar galaxy, notable for its classification as a polar ring galaxy. In this type of galaxy, a ring of stars, gas, and dust orbits perpendicular to the main galactic disk, creating a strikingly unusual appearance. Polar rings are thought to form when a smaller galaxy passes close to a larger one, depositing material into an orbit around the primary galaxy's poles. In the case of NGC 4650A, the central disk contains mostly older stars, while the polar ring is rich in gas and young stars, indicating that the ring is a site of ongoing star formation. Such galaxies are of particular interest to astronomers because they provide natural laboratories for studying the distribution of dark matter. The dynamics of the ring can be used to map the underlying gravitational potential of the galaxy, offering clues about how dark matter is arranged in systems with unusual geometry. UGC 8108, a nearby irregular galaxy, showcases another aspect of peculiar galaxies: intense internal turbulence. Observations reveal that this galaxy is riddled with chaotic star-forming regions, dense molecular clouds, and supernova remnants. The irregular structure suggests a history of minor interactions with neighboring dwarf galaxies, along with internal feedback processes like stellar winds and supernova explosions, which stir the interstellar medium and prevent the galaxy from settling into a smooth spiral or elliptical. UGC 8108's ongoing star formation demonstrates that peculiar galaxies can remain active for billions of years, sustained by interactions and internal processes that continually disturb the gas and trigger new generations of stars. In some cases, peculiar galaxies host multiple galactic nuclei, remnants of mergers that are still in the process of coalescing. A famous example is NGC 6240, a luminous infrared galaxy discussed earlier for its dust-enshrouded starburst and dual supermassive black holes. The two nuclei, separated by only a few thousand light-years, are spiraling inward toward an eventual merger. The presence of dual black holes creates strong gravitational interactions, which, combined with the intense star formation in the surrounding regions, drive massive outflows of gas at thousands of kilometers per second. These outflows shape the galaxy's evolution, quenching star formation in the central regions and redistributing material into the intergalactic medium. Systems like NGC 6240 highlight how peculiar galaxies can serve as laboratories for studying extreme astrophysical processes, including black hole mergers and feedback-driven galactic winds. Ring galaxies are another subclass of peculiar galaxies, exemplified by Cartwheel Galaxy. This galaxy features a nearly perfect ring of bright young stars, surrounding a relatively empty core. The ring is the result of a head-on collision with a smaller intruder galaxy, which sent a density wave rippling outward through the disk. As the wave moved through the interstellar medium, it compressed gas and triggered bursts of star formation along the expanding ring. The Cartwheel Galaxy offers an extraordinary view of a galaxy in mid-transformation, providing evidence of the speed and scale at which gravitational interactions can reshape entire galaxies. Peculiar galaxies can also display spectacular jets and outflows. While superwinds like those in Messier 82 are common in starburst galaxies, some peculiar systems host enormous relativistic jets powered by central black holes. For example, Centaurus A not only has a prominent dust lane, unusual for an elliptical galaxy, but also drives powerful radio jets that extend hundreds of thousands of light years into intergalactic space. These jets carry enormous amounts of energy, influencing the surrounding gas, and even affecting star formation in neighboring galaxies. The combination of dust lanes, active nuclei, and radio jets makes Centaurus A a prime example of how a peculiar galaxy can be shaped by both external interactions and internal energetic processes. Beyond these spectacular cases, peculiar galaxies also include ultra-diffuse galaxies, which are surprisingly large in size, but have very low stellar densities. Some ultra-diffuse galaxies may be the remnants of tidal interactions, where stars have been stripped away and spread over enormous areas. These galaxies challenge traditional ideas about galaxy formation and show that morphology alone is not always a reliable indicator of a galaxy's mass or evolutionary history. Peculiar galaxies are, in many ways, cosmic storytellers. Each distorted arm, tidal tail, or unusual feature encodes the history of interactions, mergers, and internal processes that have shaped the galaxy over billions of years. By studying them across multiple wavelengths, from radio to X-ray, astronomers can piece together the sequence of events that led to their present state. These galaxies remind us that the universe is not static. It is a dynamic environment where gravity, collisions, and feedback continuously reshape galaxies, creating the astonishing variety of forms we observe. The diversity of peculiar galaxies also emphasizes the importance of timescales in galactic evolution. A galaxy may appear peculiar for only a fraction of its lifetime, undergoing a burst of star formation, a merger, or a collision, and then slowly settling into a more conventional spiral or elliptical morphology. This transient nature makes peculiar galaxies rare in any snapshot of the sky, but it also makes them uniquely valuable for understanding the processes that drive cosmic evolution. Each peculiar galaxy is effectively a laboratory in real time, allowing astronomers to witness, rather than infer, the mechanisms that govern the growth and transformation of galaxies. Peculiar galaxies are not just local phenomena. Deep surveys with Hubble, JWST, and ground-based telescopes have revealed that galaxy collisions and unusual morphologies were even more common in the early universe. Many high-redshift galaxies appear irregular, clumpy, or disrupted, suggesting that peculiar forms were a standard stage in galaxy assembly when the universe was younger and mergers occurred more frequently. Studying nearby peculiar galaxies thus provides a bridge to understanding the chaotic processes that dominated the early cosmos, offering a window into the mechanisms that built the vast and diverse population of galaxies we see today. Peculiar galaxies represent the universe's most dynamic, chaotic, and fascinating laboratory. From interacting pairs and merging spirals to ring galaxies, dusty ellipticals, and ultra-diffuse systems, they demonstrate the transformative power of gravity, collisions, and feedback. Each one tells a story of cosmic evolution in action, capturing the processes that shape the cosmos on scales far beyond what our eyes can see, yet illuminating fundamental truths about how galaxies grow, interact, and ultimately change over billions of years. Peculiar galaxies are, in essence, the universe's experiments writ large, revealing the forces that sculpt galaxies, and by extension, the structure of the universe itself. Long-term evolution of cosmic structures. The universe is expanding, and that expansion has profound implications for the future of galaxies. Over time, As space continues to stretch, galaxy clusters will move farther apart, the cosmic web will become more diffuse, and eventually, individual galaxies will become isolated islands in an ever-growing void. Understanding the future evolution of galaxies requires understanding not just how galaxies work internally, but how the large-scale structure of the universe is changing over time. In the near future, on cosmic timescales, meaning the next few billion years, the most dramatic changes will occur in our immediate neighborhood. The Milky Way and Andromeda galaxies are currently approaching each other at about 110 kilometers per second, and they're on a collision course that will culminate in a merger about 4.5 billion years from now. Computer simulations of the collision show that the first pass will be relatively gentle, with the two galaxies interpenetrating and passing through each other. But gravity will pull them back together, and they'll collide again and again over the next billion years, each pass becoming more disruptive as the galaxies lose energy and spiral inward. Eventually, about 6 billion years from now, the Milky Way and Andromeda will complete their merger, forming a single giant elliptical galaxy that astronomers have nicknamed Milkomeda. The spiral arms of both galaxies will be destroyed, their disks disrupted, and their stars scattered into a three-dimensional elliptical distribution. Star formation will peak during the merger as gas clouds collide and compress, then decline rapidly as the gas is used up or expelled. What remains will be a red, dead, elliptical galaxy filled with old stars, similar to the giant ellipticals we see at the centers of galaxy clusters today. But these projections assume that our current understanding of physics and cosmology is correct, and history teaches us to be humble about such assumptions. Dark energy, the force driving the accelerated expansion, is poorly understood, and its properties could change over time in ways we can't predict. New physics might emerge at energy scales we haven't explored. The nature of dark matter might turn out to have unexpected consequences for the long-term evolution of galaxies. While the broad outlines of the future seem clear, the details remain deeply uncertain, and future discoveries may reveal surprises we can't currently imagine.